All right, welcome back to the main stage. Our first speaker for this session is Tal Duray, and he'll be telling us about scaling Zcash with Tachyon. Take it away, Tal. Yeah, half an hour. Unless you want 5 minutes of Q&A. So we can do 25 plus 5.
Okay, so hi, my name is Tal. I'm a cryptographic engineer working on Tachyon, and I'll talk about scaling Zcash. Oh, sorry. I'll give a holistic update into Tachyon, what it is, how the construction works, and then a semi-technical overview of Ragu, our proving system and PCD toolkit, and then some applications that Ragu enables for Tachyon. Things like shielded transaction aggregation, pruning the nullifier set via a third-party intermediary we call an oblivious syncing service, and some other cool applications that I think are unique to Tachyon. Oh.
I think it's a bit jammed, so you just...
Next? Okay. So at a high level, Tachyon is many things, but it in some sense realizes the vision of recursive composition outlined all the way back in the 2019 Halo paper. Tachyon basically enables recursion, which enables blockchain scalability. The recursive capabilities of Tachyon don't currently exist in the Halo 2 library, and they don't exist in production in Zcash in any capacity, which I think is a good data point that outlines like the sheer complexity of trying to inject scalability into a privacy solution and private payment systems like Zcash. Because the Halo paper came out in 2019, and only now we're trying to do some kind of recursive composition in Zcash. Tachyon is the fourth shielded pool in Zcash's history. It's basically a protocol upgrade in the same lineage as Sprout, Sapling, and Orchard, and there have been many upgrades in between. Tachyon is a scalability upgrade, and it positions itself purely as a scalability upgrade. All of these shielded pools have something called ledger indistinguishability. It's a security notion where you can't distinguish between different transactions. In the shielded pool, they're basically just opaque byte strings, and Tachyon maintains that ledger indistinguishability property. Oh my God. In terms of scalability challenges, anonymous payment systems derived from zero-cash or zero-cash-like protocols basically have the same scalability challenges. They have the shielded sync problem, so you can't query a public-facing remote RPC. All client devices and wallets need to download. They need to download all of the ciphertexts for every node payload and trial decrypt that node payload to discover a payment. There's this idea of transaction bloat. So the proofs are quite large. They're a few kilobytes in size, which bloats the transaction, which then bloats the block. You also have this nullifier growth problem. So you have runaway state growth as the nullifier state becomes large. And Tachyon solves all of these problems, or it will solve all of these problems. But I'll try to motivate specifically the last one, this nullifier growth problem. So a nullifier is basically just a revocation token. It's a byte string to prevent double spends. In Zcash, we store nullifiers in a B-tree set. And there's a paper by Sean and Ian called A Note on Notes Towards Scalable Anonymous Payments via Evolving Nullifiers and Oblivious Synchronization. they give an example in this paper that at 100 TPS, the nullifier state grows by about a gigabyte per day. If you then extend that and you shift the Overton window towards commercial payment systems like Visa, then the nullifier state grows by 500 gigabytes per day. And that's obviously untenable growth. We can't expect a client device to have the bandwidth capabilities or the compute capabilities even near that scale. So nullifier growth is a problem as the TPS grows. It grows proportional to the number of transactions. This is also state growth. Oh, thank you. This is also state growth. There is a distinction between state versus history growth. If this was history growth, that might be okay if eventually Zcash becomes like a Mina-style blockchain and we have a succinct blockchain comprising of one proof and you can just do away with all of that history. But again, this is state growth, which means all full nodes need to maintain this set and query this set. All validating consensus nodes need to maintain this. So it's a bottleneck as you increase the TPS. So I will, as an aside, also just highlight the cost differences between anonymous payment systems and non-private payment systems like Bitcoin. So in Bitcoin, and the paper talks about this as well, you only have to check a UTXO status and verify an ECDSA signature. In Tachyon, we have costs that are comparatively a lot more expensive than that. Like verifying a zero-knowledge proof is much more expensive than checking an ECDSA signature. And again, we also have this nullifier growth problem, so our costs are much higher. So the solution that the paper outlines is this notion of an evolving nullifier. So it's the idea that nullifiers evolve over time, and in Zcash now, nullifiers are associated with a note commitment. They're deterministically derived from a note commitment, but in Tachyon, they're not deterministic anymore. They're associated with an epoch. So evolving nullifiers effectively split the ledger into a collection of epochs, and to prove that a payment was unspent or that a note was unspent, you basically prove that all of the versions of that nullifier are also unspent. And we can outsource this check to a third-party intermediary that we call an oblivious syncing service. So the client device doesn't do this. This third-party OSS does this. So what is the oblivious syncing service? It's a technique that allows a remote service to prove on behalf of a client that their funds are unspent. It does many things, but at a high level, it generates a succinct proof that for non-membership for nullifiers. The client device can okay, I won't go too much into the complexity of what the OSS does because Sean has a very nice ZCon 6 talk on this. But at a high level, what the OSS does is it syncs notes and it syncs witnesses on behalf of the client. And I guess to build a mental model of how the wallet interacts with this OSS, the wallet starts up, it generates some nullifiers, and set non-inclusion witnesses. It can hand this off to the third-party OSS. The OSS can sync those notes and update those witnesses, and then the client device can take this evolved nullifier and the PCD proof that the funds are unspent and fold that via PCD into their transaction. Again, it does a lot more than this. This is just a high-level summary of what it does, but Sean has a good Zcon 6 talk on this, which I'll leave just for a few seconds if you want to watch that talk at some point. Find me after. I can hand out this QR code. So how do we go towards scalable planetary money? We want to maintain some bounded state, so full nodes should not need to maintain this perpetually growing nullifier state. Ideally, you can prune that state via the OSS, so you don't need to maintain all of the history of nullifiers on-chain. You only have to maintain the latest state of nullifiers and check that they're unique in the latest block. And you can prune all of the rest of the nullifier state. We want shielded aggregation. The idea that you can reduce transaction bloat by recursively combining proofs, which increases the block capacity. And we want every node to be a light full node. So that enables succinct blockchain constructions. The light clients become full nodes. The idea of a full node in this context is instead of syncing the whole chain, you can just verify a single proof that the blockchain history is correct. So what makes Tachyon different from other pools? This can be a talk in and of itself, but I'll motivate a high-level idea of what the distinction between our pool is and previous pools like Orchard are. In previous pools, you had a very tight coupling between the shielded protocol and the payment protocol. So the key structures were pretty complex because they had to do they had to have a lot of capabilities baked in, like spends and incoming and outgoing payment detection. Tachyon effectively decouples the shielded protocol from the payment protocol. So the shielded protocol is for snarks and encryption and the actual cryptography, and the payment protocol is a different design space for things like addresses, the UX, the key exchange. And the nice thing about decoupling them is you can work on them at the same time. So we're building the recursive proving system and PCD toolkit in the shielded pool, and we're also working with a very talented team led by Dave Oja. And they're working on many kinds of problems like a post-quantum UX, post-quantum key exchanges, things like PIR to kill shielded sync, and so forth. So Ragu, at a high level, is our proving system and PCD toolkit. It's one of the main components of Tachyon. It sits at the heart of Tachyon and does all of the heavy lifting. So Ragu specifically is a recursive snark. It uses an accumulation scheme similar to the one defined in the Halo paper. And it uses that accumulation scheme to instantiate an efficient recursion scheme. So Halo defined this notion of nested amortization. Nested amortization is it's a aggregation technique, loosely speaking, instantiated over a polynomial commitment scheme based on inner product arguments. So Ragu is Halo plus this BCLMS21 idea of split accumulation. So Ragu uses accumulation in the sense that instead of verifying proofs, we can fold them together using linearly homomorphic Pedersen commitments, and we can combine them using Fiat-Shamir. And then you can accumulate various kinds of arguments based on expensive polynomial evaluations and many other kinds of arguments. And you can defer expensive checks. and then you do a decision procedure at the end that does the expensive linear time verification. So we're just accumulating tons of expensive claims and verifying once at the end. This is also the same underlying cryptography that exists in Halo. It's the same primitives from 2020. So we didn't invent any new crypto. We're using battle-tested primitives that we're very familiar with. And Sean has a good blog post on Ragu. In terms of the core architecture, this is an R1CS-like arithmetization. It's R1CS-like in the sense that it's a Boodle-style arithmetization, like Sonic in Halo. We have a cycle fold style folding and accumulation scheme. We have a modified IPA, modified bulletproofs IPA for the commitment scheme. It's a custom IOP, so it's a custom R1CS NARC using split accumulation and IPA style commitments. And it's instantiated over the PASTA curves, the Pallas and Vesta curve cycle. In terms of the curve cycle approach that we took, there are two kinds. There are alternating and non-alternating. So alternating are like classic IVC, where you bounce between the curve cycles and you maintain a proving system on both, but you only operate on one at any given time per PCD step. Then you have lopsided, so you have one curve that's used to just get around the curve cycle. So one of them is a helper, but you still bounce between the curve cycles. Then you have non-alternating, that's things like cycle fold. So you have one curve that handles all of the scalar moles, so it does the folding, and then you have the other curve cycle that does the main circuit logic. Ragu is effectively a hybrid between cycle fold and lopsided. So we maintain simultaneous state on both curves at the same time. So we're not bouncing between the two curves. We're operating on both curves at the same time and doing work on both. So both curves have a full proving system. It has lopsided influence in the sense that the two curves are symmetric, but their workload asymmetric. So cycle fold is maximally asymmetric. You have one curve that does just the scalar moles and one curve that does the full circuit logic. So it's maximally asymmetric. Ragu is also asymmetric, but not as asymmetric. So it's a combination of different cycling approaches. In terms of the arithmetization, this is an R1CS-like arithmetization. We don't have any complex, newer machinery that new folding schemes like Nova or CycleFold use. We don't have multilinear polynomials. We have just univariate polynomials. We don't have lookup arguments, no custom gates, no high-degree gates. So it's a very simple arithmetization with univariate polynomials. We also don't have any pre-processing. So pre-processing in this context means something like Marlin or Planck, where you commit to a fixed collection of polynomials and you embed those commitments in a verification key, and then you can open like KZG commitments against those pre-committed polynomials. So we don't do that. We actually have a post-processing approach, which is different than that, and I think in our context more efficient. We also don't have any verification keys, so we don't need to launder verification keys between the recursion circuits. We don't reason about the full R1CS matrix, so we don't materialize the full set of R1CS constraints. We have these lightweight circuit objects and evaluate the polynomials at partial restrictions, but the full R1CS matrix is never evaluated in memory. We don't evaluate polynomials directly during synthesis, so we want the reduction to polynomials to be highly optimized and, again, not store large polynomials in memory. We can take advantage of memoization. So we have this notion called a routine. So if the same subcircuit appears multiple times, like the same endoscalar operations or the same Poseidon hashes, you can effectively memoize those operations. So those operations can use the same polynomial, and it's effectively a scaling relationship. So instead of recomputing the polynomials, you can just shift the polynomials and memoize them. We also need highly efficient circuit synthesis code. So circuit synthesis is a hot path that we need to optimize for. If you look at something like ArcWorks, they bundle witness generation and constraint synthesis. We don't do that. We have witnesses are optional depending on the synthesis path that we take. So in ArcWorks, circuit synthesis is consistently 25 to 30% of the proof generation time. I haven't fully benchmarked what it is in our system, but circuit synthesis does need to be highly optimized, especially in a non-uniform PCD setting where you're switching between nodes in the PCD graph very often. So the optimization trade-off, I guess a natural question is, like, how does Ragu compensate for having such a simple arithmetization? Well, it boils down to the things we actually optimize for. We optimize for verifier speed, which scales with the size of the circuits, not the number of circuits. And we also optimize for the option of the number of circuits we can choose per PCD step, and we want that to be large. Don't know how much time I have, so I'll just skip some stuff. So why do we want smaller circuits? Well, it means smaller witness commitments, which leads to smaller IPA proofs, which leads to smaller verifier multi-exponentiation. So we want the verification to be fast, and that's what we optimize for. We also want the verification to be fast because of things like propagating transactions or like block transaction times. So like nodes need to verify before forwarding, and if the verification is slow, then at some limit that can equal network latency. So we want the verification to be fast, and for block times, verification time effectively puts a limit floor on how low the block times can be. There's also this notion called a recursion threshold. It's the minimum statement required to perform recursion. So when a proof system is fully succinct, so meaning the proof size and the verification time are sublinear, the system can verify its own proofs. We have a recursion threshold of 2 to the 11 gates. The verification scales with 4n linear constraints, so we're doing 2 to the 13 MSMs. We have this concept called a registry polynomial. So you can encode all the circuits in a single polynomial, and then you can evaluate the polynomial at different roots of unity over a domain and recover the specific circuit polynomials. So we instantiate this trivariate polynomial MWXY. You can evaluate that at some root of unity and recover the bivariate SXY. There's a post-processing that we do to this polynomial. So we evaluate this polynomial at a set of points that overdetermines the polynomial, and then we can take a registry digest of the polynomial and embed that as a constraint in our polynomials during polynomial evaluation time. So if you tweak the polynomial degrees of freedom, if a malicious actor tweaks them, that'll change the polynomial evaluation, which changes the registry. Well, it changes the registry key constraint, which changes the polynomial evaluation. So you can't know ahead of time what the polynomial will evaluate to, because any change will again modify that polynomial. We have this notion called a staging system. So usually you commit to the full witness, With staging, and this is a known technique, we can commit to stages. We can commit to witnesses in partial stages. So a stage is a collection of wires that's shared by multiple recursion circuits, and they can share those stages. It's used in two contexts in our proving system. You can commit to each stage independently and absorb commitments, and then you can squeeze challenges from those commitments. So you can absorb interstitial commitments and squeeze challenges. We also use it to reduce hashing. So if you need to encode like n things in a Fiat-Shamir transcript, you can put those in a stage and commit to that stage. We call this a nested commitment. So you're committing to one thing instead of n things. I don't have a lot of time, so I'll skip this. So the thing we actually defer are well-formness checks, verifying that the nested staging polynomials don't overlap, that the wire stages are non-contiguous, and we defer all of the scalar multiplications. Okay, quickly talking about applications, you have this. The obvious application is shielded aggregation. So instead of putting n transactions in a block, you can recursively compose them into a single transaction. The OSS can use this recursive capability to generate these nullifiers and to update them over time. In the whole construction of Tachyon, we're probably not going to have any Merkle trees. We have arity to PCD, that's dynamic depth, but we don't need any like special set accumulators. It's just a hash chain. The main technique that's not highlighted here, it's called polynomial oracle access. So it's this idea that the application has access to the underlying univariate polynomial commitment scheme, and it can open the commitment scheme at any point the application needs. And you can build like very complex IOPs that are generic, that don't even have to be snarks. You can build IOPs for things like volatile memory checking to check that an application accessed memory correctly, and the shielded protocol can use that to check things about nullifiers and commitments. We're also formally verifying parts of Ragu. We're working with ZkSecurity to integrate their clean framework, their lean DSL against Ragu circuit API. As of now, as of this morning, we do have a blog post on this. Quickly, again, post-quantum can be a talk in and of itself, but I'll just give a quick summary. We are post-quantum today in most cases because we do use symmetric primitives. But to be fully post-quantum sound, we need to move from an elliptic curve-based PCS to a lattice-based PCS. And if you look at the lattice literature, they're settling on polynomial commitments. So when Zcash has post-quantum primitives, we can just swap the PCS. In terms of encryption, we'd need to go from elliptic curve chems to post-quantum chems, ML-chem, and post-quantum signatures. We have a ton of like post-quantum resources, like a podcast, a roadmap, a thing called quantum recoverability, so like freezing the shielded pool in the event of a quantum adversary. We have a blog. We do plan to have a protocol upgrade and a testnet sometime later this year. This is our team: Sean, myself, Connor O'Hara, Alex Jiang, and Elle Winslow. And then we do have a website, tachyon.zcash, and Tachyon Zcash is the GitHub if you want to learn more. And if you have any questions, email Sean. Thank you.
Thank you very much, Tal. Unfortunately, I don't think we'll have time for live questions, but Tal, will you be available for questions offline? Yeah, amazing. Great. Our next speaker is Emanuele Ragnoli from Provably, and he's going to be telling us about snarks or not snarks for databases. There you go. If you stay within this line, you'll
so
be
I have
on
to stay on this side.
Exactly.
Okay.
Yeah.
Awesome.
And then the pointer is there.
1, 2, 3. Hey, the last talk before lunch. Yeah. So I'm going to talk about databases, and especially the idea of having expressive and modular databases. This is work that has been accepted at ACM CCS 2026, and it's work between myself, Vincenzo Botta, Simone Bottoni, Matteo Campanelli, and Alberto Trombetta, and it's collaboration between Provably Technology, our startup, Off-Chain Labs, the University of Tartu, the University of Warsaw, and the University of Insubria. And we don't have a timer here, right? Okay. Now, usually you start with motivation, so the typical one, why did we do it? Because we liked it, but also because it's quite important to have verifiable databases, especially in this era of privacy, AI, and multiplication of data. So databases, as a matter of fact, run the world. They are sort of considered, the poor stack of the IT framework, but as a matter of fact, it's where data sits all the time. There is a bit of echo, by the way, over here. Yeah, okay. They are important in financial system, scientific data, social platform, government records, and most of the time they are outsourced. So, and that creates what we call the trust problem. So, and the trust problem is we trust the provider of a DB with our data to do 2 jobs. The first one, to stir the data correctly, and the second one, to execute the queries correctly. So what happens if the database provider lies, or if there are some bugs, or if it gets compromised? Verifiable database is an idea that was already authored by Ostrovsky, Rakov, and Smith in 2024. I don't remember exactly the title of the paper, but it's something like efficient computing, etc., etc. But the idea of Ostrovsky et al. Was the client holds only a short digest, delta DB. For every query that the client does to a verifiable DB, the data owner, the database provider, attach a succinct proof pi that is verified then, and then the verifier verifies with the delta DB, the query gives an answer, the proof pi, and then the answer is accepted or rejected. And if it is rejected, some misbehavior is caught. What was the overall goal, and the important goal here is that the proof needs to be succinct, it needs to be non-interactive, and the verification must be public. Why non-interactive? Because we are not really doing streaming or a line, etc., etc. DB most of the time is a static entity that is hosted somewhere. Why it matters in practice? Because, especially for financial reporting, the regulators required regular reporting of data, but also of statistical analysis of the data, for example, to the SEC. For data market aggregators, untrusted aggregators need to certify SLA-style claims, like the record has been updated in the last 24 hours. For blockchain oracles and analytics, like off-chain data must reach a smart contract and then automatically import it into the execution of the smart contract, and after proof that have been untampered. And anywhere that there is outsourced storage that meets analytical queries. Simplicity matters too, because simpler designs are easier to audit, easier to maintain, and historically less vulnerability prone. What is a verifiable database? It's really for probability polynomial time algorithms. So we have a setup, usually the typical tau setup, etc., for case AG. That is actually what we use. The setup produces a key for the prover and a key for the verifier. There is a preprocessing algorithm in which inputs like the prover key and the database, outputs a commitment, a digest of the database, and the state that is on the server side. A query is then run. The answer to the query is given as A with a proof pi, and that is then verified. We then accept or reject. This proof needs to satisfy the requirement of completeness. That is, if I have a honest server, the verifier accepts the answer always. Soundness, that is, if the adversary makes the verifier, no polynomial time algorithm adversary makes the verifier accept the wrong answer. And last but not least, it needs to be succinct. That is basically the size of the proof, and the verifier time are an O of the size of the answer plus the query. This is very important. We want succinctness in terms of verifier and proof time, and we don't want that to be dependent on the database size, because databases tend to explode. So what is the state of the art and the contribution? There are two main families of verifiable databases. One that comes from authenticated data structures. Under these, basically, past works have been using cryptographic primitives like set accumulators, vector and polynomial commitment, and Merkle-style trees. It is simple, it's well understood, and the state of the art, best prototype, code base, etc., was IntegriDB that was published in CCS 2015. And then recently, general proof systems, especially from the ZKP area, entered the arena with the SNARKs, JKR, SumCheck, zero-knowledge VMs. They are highly expressive. What do we mean by expressive? It means that when we do a query to a database, we want to have the possibility to be as rich as possible in terms of SQL. And examples are Verifiable SQL, zkSQL, Poneglyph DB, products of Lagrange, Axiom, and Space and Time. Both the families come with the non-trivial drawbacks. So the limits of prior ADS-based system, especially IntegriDB, is that they use a lot set accumulators. What is a set accumulator? A set accumulator is a cryptographic primitive that essentially proves that an element belongs to a set. So IntegriDB composed set accumulators with an authenticated interval freeze. Now, the issue with this is that a database is not only a set. A database is a composition of row, columns, alignments, etc. When we consider that only with the set operations, then, for example, we lose multiplicity. So, for example, if I have the element 10 that is in row 5, column 6, and then again at row 10 of column 6, with the set accumulators, I lose the fact that the element is reproduced 2 times. To do that, I need to increase bandwidth and to play tricks with the set for multiplicity, and that leads to the proof in growing in size. And normally this leads to quadratic preprocessing and storage in terms dependent on subject to the number of columns. There is also limited expressivity because I cannot combine columns in a row-aware way. again. So I'm just proving that the element exists. But for example, if I want to do this, if I want to prove that the sum of two elements is a certain value, that is an issue because the element was counted only once. And there is also an issue with the range proofs because, for example, it's very hard to prove that I selected certain elements, for example, bigger than a certain value. IntegriDB solves that by using authenticated interval trees, but authenticated interval trees then imply the fact that the proof eventually grows with the size of the database. That is not one of the desiderata that we had for verifiable databases. In terms, when we talk about the other families, so the limits of general purpose proof systems, we have issues with complexity. Zero-knowledge VMs require instruction decoding, memory consistency, segmentation, recursion, final snark compression. There are a lot of moving parts. There is a burden in auditing because creating circuits based on that replicate SQL queries, etc., require the circuit normally to balloon and explode. And so there is a lack of simplicity that tends to increase the threat vector when it comes to security. Now, when we started this work, the answer that we wanted to have was, can we keep the simplicity of authenticated data structure while pushing expressivity and performance like we have in general proof systems? So we came up with a new verifiable databases construction that is built from simple authenticated data structures in which we combine vector commitments and set accumulators. It's more expressive than prior ADS-based work. The proof size is independent of the database size. It's no quadratic preprocessing or storage. And the order of magnitude is a fewer line of code than ZKVM-based VDBS, a lot of fewer lines. And we also create an abstract framework to express that, and also in order to make it modular, such that we could basically swap in and out the cryptographic primitives. We wrote it in Rust. It can scale to millions of rows on a laptop. Technical overview. So this is how we constructed it. We have a polynomial commitment like a case AG. Basically, that gives the digest of the DB and guarantees that the DB that is claimed to be is the one claimed to be. We wanted to do operations that are set-like. So does a certain subset belongs in DB, etc., etc. So we have the set accumulators. But compared to IntegriDB, we don't do the set accumulators on the elements, but the indexes of the rows. This is very important because it allows us to do a lot of operations like range proofs that were not possible before in ADS type of structures. And then we needed to do operations, we needed to prove operations like sum, average, etc., etc., all the SQL type of aggregations. And for that, so basically we use linear map vector commitments with the inner product tricks. And we build everything with a compiler. I'm going to skip this. I already talked about this, basically. For example, let's consider some query. I want to select the element such that the sum of 2 times the price plus an extra fee as S from a database that is called price info. So the idea is that I treat each column as a vector that I access via Oracle handle. So in the preprocessing, the client receives a slice handles P, the price, and another one that is extra fee. The server sends the claimed answer, that is X sum of 2pi plus xi over all the i's. So the client uses those handles to form h equal to p plus x homomorphically, because that's one of the properties that we include, and it accepts it if and only if the inner product of that results with 1 is equal to the sum that has been claimed. Why is this interesting and exciting? Because this was not supported by the previous ADS structures like IntegriDB, because as we said already, so set-based abstraction are really hard to achieve the combination of columns row by row. The cryptographic translation of this abstraction is, so I have the two vector commitments, the two commitments, CMP, in which I commit the vector under PRK of P, and CMX, in which I commit the vector, again, under PRK of X. The prover answers S plus a proof pi S that has been computed using OpenLI of the linear vector commitment map. And the verifier takes those, does a sum of the commitments under homomorphism, and accept it if and only if the verification under linear verifier key, CMH, CM1, S, pi S is equal to 1. So basically, each idealized handle is replaced by an algebraic commitment, and each idealized test by a few cryptographic pairings. If we introduce also a filter like where, so we want to select the elements that are bigger than a certain value, now that's where the set accumulator comes in. So now the set S is the sum over a subset X of the number of the rows. We cannot send X in full because if the DB is very big, then the proof becomes linear in the size of the DB. That's again something we didn't want to have. But we want a succinct digest of X, and that is the set accumulators. Now the verifier must check that S is in the sum of P on the indexes in this set handle, and the set handle contains only and only the indexes with pi bigger or equal than 100. The trick to do this is that now we need the vectors and the sets to talk to each other. They are two different types of commitments. We need them. We need to be able to compose them. The framework that we built this, as I said before, is abstracted from the cryptographic primitives such that we can swap them eventually and modularize. So we have two opaque or Apple types that replace the physical access to the data. Think of them as a sort of immaterial pointers. So if you are a verifier, you get these immaterial pointers, you don't get the content of those. They just map basically to the data in the data sets. There's slice handle that points to a vector, and the set handle that points to a set. The verifier never stores the underlying object, and they capture the essential abstraction for VDB's blueprints, and they capture succinctness. And they closely follow SQL flavors, so columns to slices and row sets to sets. It's a little bit what happens with the polynomial IOPs for snarks. So we created, therefore, a framework with a limited set of operations in a RISC-style interface. So we have a set operations, like two sets are the unity, the intersection, the inclusion, the complements. We have test on slices, basically to replicate arithmetic operations using the inner products. We can get new slices from homomorphism, and we can read the data with the pre-image style of maps. I'll skip this because we are running out of time. So once basically the verifier received the SQL query, now it has to replace each handle with a commitment. So the slice, vector slice is replaced with the vector commitments, and the set slices is replaced with the set accumulators. And each idealized test becomes, for a set test, an accumulator proof. An inner product is mapped to OpenLib in LVC. A read its subvector opening again in LVC. And the homomorphism on the slice, it's a verifier local on commitment. There is one missing primitive. As we said before, we want sets to talk to vectors. So a way to test that a slice is a 0 on an accumulated set of positions. And again, this helps with the range proofs. So we created this, what is called the zero testing, in which basically given a vector commitments, a set accumulators, and the proof, we want to convince the verifier that Vj is equal 0 for all the j's that are supposed to be selected by the query. The construction theorem is in the paper, properly proved, etc. But informally, basically, we use the trick that each row index generate a quotient polynomial, x minus s, that makes v vanishes on s if and only if z s such that pv, etc., etc. And this is sound because of Schwarzschild, so the typical I sent, I tested with the random values, and it's absolutely improbable that the opposite happens. We then have compilation theorem, in which basically if I have a query family and that meets a succinct idealized VDBs, then there exists a succinct cryptographic VDB for Q from either a holomorphic VC plus a set accumulator with the right test, or any extractable homomorphic polynomial commitment. We have basically one blueprint that allows many instantiation, and again, because it's abstracted, we can swap the cryptographic primitives. We can even put in lattice-based polynomial commitments like the ones of Wang et al. In their 2024 paper. 3-4 minutes. Then I'll skip this. So there are examples of queries and how they are realized. I'll just mention this. So all the operations that we have done up to now basically support static databases. But because LVC is homomorphic, basically the vector commitments can be updated incrementally, and that basically means that VDBs can support updates and proving that an update happens. Of course, this cannot be done in O1 in the public verifiability settings, but the experiments that we have done up to now support the case that updates are practical for common patterns like insert, delete, and single cell updates. This has been implemented in Rust with ArcWorks and BLS 12381, multi-threaded prover, single-threaded verifier benchmark. It scales really well, 2 million of rows on a simple laptop. We don't need the GPUs. It's a middleware layer that plugs into a lot of existing databases. These are more or less, these are the experimental results that we have in the paper, and that show that the proof size is independent of the size of the DB, as we said, one of the desiderata, and it depends only on the query type and the response. For example, we can see there that a complex query like QMatch so gets a higher verifier time, etc. And the scalability is quasi-linear. The verifier is essentially constant. And I'll skip the comparison summary as well. And what we have shown basically is that we have built something very simple, ADS-based. It has an abstraction layer. The framework is idealized because there is a separation of concern and free instantiation. And it's simple, modular, performant, and extremely easy to audit.
Thank you very much, Manuele. Do we have any questions?
Hi, very nice talk, thank you. I'm assuming because you're committing to the database that that commitment must be stored somewhere. Where are you planning to store it and share it? Is that something you've thought about?
It's on the data owner side.
Thank you.
Thank you. Any other questions? No, everyone's hungry. Okay, so with that, we'll thank Emanuele once again. And we can now head to lunch. We'll resume, I think, at 2 p.m. Thanks.
E
I hope everyone had a nice lunch. We're going to start with the afternoon talks. Our first talk of the afternoon is by Vivian on zkID. Please take it away, Vivian.
Thank you very much for the introduction. And hello, everyone. My name is Vivian Plasencia, and I'm the zkID team lead in PSC at the Ethereum Foundation. And I will be talking about the zkID work we have been doing in research and engineering. So let's start. So zkID is the short version of zero-knowledge identity, and it's a way to prove things about yourself without revealing any other information. And you can prove things like you're older than 18, or your residency country, or things like that. So the zkID team has been working on some projects, so here you can see some of them. And one of those is the Ano@Har project. It's a zk protocol to prove @Har IDs in a privacy-preserving way. Another project is zkPDF, and this is a project where you can prove content about a PDF without revealing any other information from the PDF. And we have been working on a lot of standard efforts, like we work with the W3C and IETF, DIF, Linux Foundation, and more recently we have been working on the profile for the etc document, and I'm gonna talk about that because it's also related to OpenAC, which is a new zkID generic construction that there is a paper, and I'm going to also talk a bit about that too. And another work we have been doing is on revocation, which is a very important topic in zkID, and I'm going to also cover that. So the main motivation for OpenAC was that SDJWTs are not unlinkable. So that's what is used for selective disclosure, and they are not unlinkable because they will you will get the same proof every time you use it. So that's the main motivation for the creation of OpenAC. And OpenAC is a generic zkID construction. It's the mapping to EUDI high level. It maps the EUDI high level requirements of Annex 2, and the construction is modular. It means that it has some blocks that you can change if you want to make it post-quantum, and I'm going to talk a bit about that too. And there are different formats for credentials, and there is a specific layer for that, so it's not attached to a specific format. You can use the format you want, and not trusted setup is required. It's using Spartan, so yeah, not trusted setup. And it's compatible with existing identity systems, so the issuer doesn't need to change the signatures or anything like that. And in this link, you can find use cases for OpenAC and more information. OpenAC provides unlinkability in credentials, so you can create zk proofs, and then people, like no one, even if the verifier collude with another verifier, so they won't be able to link the proofs. And it supports device binding, which means that the issuer will issue a credential to specific holder, and then also with the verifier when the holder creates a proof. So it supports complete device binding. And it now supports, not in the paper, in the paper you will see it mentioning, but in the first version of the construction, it was focused on age verification, but now it supports generalized predicates, and I'm gonna also talk about how we implemented that. And it supports so far SDJWT and MDL and MDoc, and the current tech stack is Circom, Spartan, and Hyrax. So this is the architecture of OpenAC, and this will happen in the holder device. So the general idea of the flow for a credential is the issuer will issue a credential to a holder, and the holder will use it with a verifier or the relaying party. And then this process will happen in the holder's device. And the proof generation will be divided into 2 steps. The idea of this is to make presentations more efficient so that the proof generation will be very fast. So in the first phase is prepare, and then in this phase there will be some pre-processing and parsing of the credential and verification of signatures. So this process is completely offline, so it doesn't need to be done at presentation time. That's why presentation time is more efficient. And the show process, which is the second one, is the one that will run at presentation time, and is when the holder will prove the predicates and the things that the verifier needs for verification. And there is this reblind process to prevent linking the proofs. So here you will see the unlinkability. So the first version of the project will contain age verification. So in this second version of the implementation, it contains generalized predicates. So in the paper, you will see this you will see that this exists, but in the implementation and also we didn't have a solution for that, how we were gonna do it. There are different ways to do it, and I'm gonna talk about, but first, the predicate. So a predicate is when you want to prove something about the credentials, like for example, you're older than 18. There are also other predicates like range proofs, like you want to prove your income is in a range, or also membership, that your residency country is in a list of countries, or not membership, the same thing, like your residency country, for example, is not in this list. And you can also prove more complex expression, like you have been working for 2 years or more, and your annual income is in this range. So you can combine things and make it more difficult and more expressive too. So that's predicates, and that's what we were trying to solve, to have more expressiveness. And there are different ways to do that. And one way could be to have the set of predicates that you want and create a circuit for that and solve each one of them. Like, okay, I want range proofs. Then I'm going to create a solution for range proofs. And the same for membership. And then you will have each solution. But the problem with that is that it's not general. Like, it's just for those specific cases. Another solution would be to create a language, a new language, like a programming language for that. And then you will have parsing and all these things, like the HT3, like everything, like a compiler for that language. And then it's more complicated, but it's better as a solution. So for us, since we are using zcom and we don't want to complicate things or make it less efficient, then we did this solution, which is the mix, like it's in the middle. You can get a lot of expressiveness, but also you can get all these use cases. So I'm going to explain how it's done. So the flow will be, you have your expression, and the expression can contain parentheses or everything. So, and any logical expression, it supports anything related to logical expressions. Then the expression will be turned into a simple sequence. It's a postfix notation, so I'm going to also talk about that. And then it will be checked, and the verifier will know if it's true or false without knowing anything in the middle. And here you can read all the document, and it contains all the details. So, for example, here we have the claims, like the date of birth, the income, the country, and then you want to prove this expression. So you see that it contains different predicates and also parentheses. And what we are going to do is to take this expression and convert it, that's an infix, notation and convert it to postfix notation. So we will use Schontinger algorithm. So that algorithm, you can use it to, it's usually for math expression, but it also works for logical expression. And you can use this algorithm to evaluate the expression with parentheses and everything, or you can use it to convert to postfix notation. And in this case, we are using it to convert to postfix notation because we want efficiency in circuits. So it's more efficient to go from left to right to check everything, and then we don't have to, we have the expressiveness of the parentheses, but we don't have to manage parentheses in the circuit. Then how this is done is that there are also two steps here, and the predicates are with you are greater than and things like that, comparing things. And then in the second part with this logical expression, you have and, or, and everything related to the logical operators. So having these predicates, then they will be evaluated. So that's the first step. Take all the predicates and evaluate them. And then the second step will be to evaluate the full expression in postfix notation. And so the steps are like in the first step, you have already true, false, and everything. So now you just have to, with your logical expression, you just have to evaluate that. And then it will be like a stack. You, like the Schontinger algorithm, it works like that. You read the first, in the expression, you read the first predicate, and in this case, it's true. Then you push the true, and then you read the second predicate because it's the next element in the expression. It's also true, you push true. Then you will go to the end, and it's a logical expression. You will take the last two elements and evaluate them and push the result. And now you will have true there. And then you will read the next token, which is false. And then the other one is or. You will pop both and then evaluate that. And we have true as the final result, and that's what the verifier will know. The verifier won't see the other things. They won't see if one was true or false. They will just see the final result. So that's the solution we did for predicates, but apart from that, that's the solution for OpenAC to evaluate predicates, because before it was just calculating the age and checking if it's older than 18. And then another thing we worked on was revocation. And revocation is a very important part for identities, and it's the process that allows an issuer to invalidate a previously issued credential so that verifiers can check if that credential is valid or not. And we did a lot of research on that and mainly focus on Merkle trees. And here you can find the article with all the benchmarks and all the details and everything. And we collaborated on that with a report with the diff team. And here you can find the report, so more people work on that too. And as a solution, like as a summary, main takeaway from this research was that non-membership proof in a list of revoked credentials is the most efficient way, because for Merkle trees, there were two solutions. One, if you prove membership in a list of valid credentials, and then it means that your credential is valid. And the other is if you prove non-membership in the list of revoked credentials, then it means that, okay, it's valid because it's not in the list of revoked credentials. So following that, then the next step was like, what is the most efficient Merkle tree for non-membership proofs? And then we needed to use that, right, for revocation. Then we want to integrate this feature, and then we needed to find that. And there are two popular solutions for non-membership proof in Merkle trees. One is sparse Merkle trees, and the other is index Merkle trees. And we wanted to have like an efficient way. And we know that SMT is actually very popular, but the tree depth is really long to prevent collisions, and it's not super efficient if you want in ZK. It works well, but it's better to not have this depth if you want to use it in ZK. So then we wanted to have like a more efficient solution. And in this case, in the index Merkle tree is actually very good because you just use the tree depths that you need. And you don't need like this long tree depth. And that's why it's kind of like for ZK, a more efficient solution. And at the same time, index Merkle tree is using a normal like Merkle tree with specific depth. And for Semaphore, some time ago, we created the LinaMT, which is an efficient tree for membership proof. And in this case, it doesn't support non-membership proof. So we needed to find the most efficient way from membership proof and also for non-membership proof so that we can get the best from both worlds, and that will be the most efficient tree for non-membership. So that's, we created LinaMT Plus, which is LinaMT with the non-membership feature, and taking the efficiency from the LinaMT in the tree creation, and then taking the non-membership feature, the efficiency in non-membership feature from the index Merkle tree. So you can find here the implementation and more information. So this is a normal LinaMT, but in this case, it will have the feature of non-membership proof. So if you want just membership proof, just use the normal LinaMT. But if you want the non-membership proof, you can use this one. And so how it's done? Usually for non-membership proof, where you are proving, like in membership proof, you prove that your element is in the tree. How you do that? So you know that your element is a leaf, so then you have the Merkle proof and you create the fruit, and it's the same fruit as the tree, so everything is fine. But what's the problem with non-membership proof? So how do you prove that? So the idea is that you should be somewhere in the tree, in the leaves, and you are not there. So that's the general idea. For the SMT, it's like your index you take your index and you should be a specific position, and you are not there, that value is not there, so that's the way it proves non-membership. And in the case of index Merkle tree, the way it will be done is that you have the list will contain the value and the next value, and then your value should to be there. It should be a leaf, and if you know that there is a leaf with a smaller value and the next value is bigger than yours, then it means that you are not there. So then you will take the membership proof of that specific leaf. So we do the same, like we took this idea from there, because for non-membership proof, you always need a way to have sorting or something. So then we don't take the other elements, we will just take the value and next value. And there is this auxiliary node to prove non-membership for the first element you insert. So that's the tree we will use for revocation, and that's more efficient than normal non-membership proof trees. And apart from that, we also started to work on the SDK so that people can easily integrate the solution. So this is a work in progress. We plan, since we are adding more features, we plan to add more features to the SDK as well. So just for you to have an idea of how it will work, but this is a work in progress, and we will continue adding more features to the SDK. So from the paper, you can see benchmarks. Also in the resources I'm going to share, you can check the latest benchmarks, but you will see that this is for age verification, just like in phone, and you will see like proving time, prevalent time, verification time. So this is fine for real world usage. So yeah, it's like pretty efficient. So what's next for OpenSC and zkID? So now we want to integrate multi-VC linking and also issue hiding, so that in the multi-VC linking, so you can link you can get expressions from different credentials, so verifiers can ask about different credentials. Issue hiding is to hide the issuer to the verifier, because sometimes that's necessary. and also the OpenAC profile. So OpenAC is one of the solutions for the European EUDI wallet. So we have been working to create this profile because it will be added to the Etsy document, which is the document containing these specifications. So yeah, we have been working on that. So you will see this soon. And we will also work more on developer experience, so that it's easier for people to use it. Right now, there is a demo and web, like a phone, and with the SDK, you can use it in web, but we want to make it easier. And also, there will be a new version of the paper with this latest research, and where we finish with multi-VC linking and more like issue hiding. So we plan to explain all that too in a new version. And we have been also working on a bit on post-quantum OpenAC. The work will start soon, like more work, but we already started a bit on that because the idea is to have a post-quantum OpenAC. And that since OpenAC is modular, we plan to migrate all these modules to be post-quantum. And we also want to explore public registry, the ID infrastructure on Ethereum. So we want to work more with ID teams working on Ethereum and to see how we can help. So please, if you work on something like that, let me know and contact us. So I would love to help more on that. So you can see the zkID roadmap here, and it contains these elements. So here are some resources. So OpenAC Studio is for you to see use cases, and this is the paper I was talking about. So check it out. And this is the GitHub where we add all the research and documents. So thank you very much. And if you have any questions, please let me know.
We have time for questions. Yep.
Yeah, so what will be the use case of the implementation of using the OpenAC SDK? Like, let's say I have an IDP, which is an issuer. Like, how do you see using the OpenAC SDK in an IDP that it's issuing credentials, just to understand this scope?
Yes, so OpenAC is more like generic for any credential, and so it's more it will run in the holder, and for use cases, it will be like the age verification. So if your credential contains your date of birth, for example, you will be able, with this, you will be able to prove that you are older than a specific number without revealing your date of birth or any other information in your credential. And then the verifier will know that you are older than specific number, but without knowing anything additional.
And does the SDK needs like any external connection or Web3 connection or something, or a specific deploy contract or something like that, just to?
No, not contract now. And we did actually some research on that, but Spartan, yeah, so there is not verifier on-chain, and it won't probably be efficient. But that's something that we also would like to have. But so, not contracts.
Okay, perfect. Thank you.
I think there's another question over here. Yeah.
Hey, I don't know if I missed it, but you mentioned unlinkability and revocability. Is there also something against replay? So like, let's say I have a credential, I use it to generate a proof that I'm 18 or more. What if I give my proof to someone that is not 18? Can they verify, or is there a mechanism that prevents these kind of things?
Yeah, so device binding. Okay. So this system will make sure that your proof was generated in the same device that the issuer used to issue the credential. And then the verifier will verify that. So yeah.
Okay. More questions? No? So with that, let's thank our speaker once again. Our next speaker is going to talk to us about security and computers and billions of dollars. Please welcome George Kadianakis.
Hello everyone. So I'm George. I work on the Ethereum Foundation cryptography team, and today I'm going to talk about the work we've been doing on securing ZKVMs. Yeah, this is a team-wide work. The cryptography team has been working on this. It's not my work, but still I present it. So yeah, let's move forward. So I think I should motivate a bit this talk, why we're talking about ZKVMs. The answer is that ZKVMs are just to explain why we're looking at funky images. Well, everything, the images are all from Rome. So you can go around the city and see I don't know, like the sculptures and the things. I'm not Italian, so this doesn't make much sense, but still, like, the aesthetics are Rome inspired, so yeah, anyway, let's continue. So, yeah, so where was I? So ZKVMs are particularly nice for Ethereum because blockchains are fundamentally bottlenecked in the sense that validators of decentralized blockchains, at some point, they're not able to follow the chain if it gets heavy enough, if it gets big enough, if enough transactions are in every block. So ZK proofs and ZKVMs flip this around, and it essentially allow validators to verify a very succinct proof very fast and essentially follow a very heavy chain very efficiently. So it basically resolves one of the fundamental bottlenecks of blockchains, and that's why Ethereum is so interested in ZKVMs all of a sudden. Anyway, moving forward, ZKVMs have been an interesting topic for years, but the performance of them has been a big question. So a bit more than a year ago, the Ethereum Foundation started looking at the performance of ZKVMs to see if a ZKVM can actually prove fast enough to follow the Ethereum chain. And this was a blog post that was done that sort of set up some goals in terms of performance, in terms of prover costs. And the answer, after lots of months of the teams working on it, was a very big success. Prover costs dropped many X's, prover hardware costs dropped a lot. Basically, through this real-time proving initiative, the ZKVMs on L1 were de-risked, and it stopped being an issue of performance anymore. And I think now it's more an issue of security, in the sense that we know that ZKVMs can prove fast enough, but the question is if they can prove secure enough. And it's a good question, to be honest, because I don't think it's like a stretch to say that ZKVMs are an extremely complicated cryptographic object, to the point that I don't think humans know how to deploy such complex objects on the internet right now. I think it's probably the most complex cryptographic object that is seriously being considered getting deployed. And the security repercussions of it getting hacked are huge, in the sense that if you hack the L1 ZKVM, you can essentially do an illegal state transition on Ethereum, and this means that you can do many, many bad things as yeah, it's basically a huge issue. So we need to think about security seriously, and this is a talk on the security of how we think about security of L1 ZKVM, mostly on the proof system layer, on the polynomial commitment layer, not so much on the implementation side or on the formal verification side. I think it's worth doing a talk about the holistic thing, but this talk in particular is going to be focusing mostly on proof system and the foundational layer stuff. Nico, I don't have a timer thing. There is no timer. Okay. Okay. All right. So in the beginning of this year, we did this blog post, which basically sets, again, some limits, some goals for how we see the proof system security going forward. And it's going to be an initiative that lasts this entire year, 2026. And it sets up some goals. So I'm going to talk a bit about these goals, and then I'm going to talk a bit about what it's May now, so a few months have passed. So I'm going to talk a bit about the journey so far. Right, so the first goal is to is for ZKVMs to get to 128 bits of security. This doesn't seem like such a controversial goal in a wider industry sense, because the wider cryptographic industry thinks about 128-bit security as the normal thing. You know, like when you think about ciphers, symmetric crypto, everything is tuned to 128-bit, but ZKVMs have been traditionally allowed to exist in like 100 bits, 80 bits, 80 bits conjectured security, which I'm not even going to touch so much right now on. So like, you know, like basically we have given like a bit of an artistic freedom to ZKVMs due to them being so complex, but now we sort of want to take it back and be like, you know, this is serious stuff. Ethereum is a serious business, like, you know, like security of Ethereum is serious business. And also, you know, like if we want ZKVMs to find product market fit outside of blockchains, like I think the other industries will also want 128-bit security. So this is the first goal. The second goal is that if you have looked at ZKVMs, they all have this very complex recursive structure where, you know, it's not like just a simple IOP or whatever, like it's like a small proofs, recursed, and then you get a final proof after lots of complex architectural thingies. What we want, and this, you know, like we know how to prove the small components, but we don't know how to prove the entire thing. So one thing we want out of this project is by the end of the year to be able to have a security proof for the entire thing, which we believe is going to illuminate lots of hidden details of the proof architecture that are currently hidden. Right, so that's the second goal. And the last goal, in a sense, is that we're doing these things now because the proof system layer is the foundation of the ZKVM. So if we get serious about the foundational layer and it freezes and it ossifies because it gives us what we want out of it, this will allow us to start working seriously on the layers above, which is implementation, formal verification, these kind of things that we're currently working on. But I think when the bottom layer is frozen, it will give us, you know, we can invest more because we know that it's not going to change. So yeah, these are the three goals of this year's security sprint. And now I'm going to talk a bit about, you know, it's May now, so a few months have passed. So I'm going to give like a bit of what happened. Can I have a bottle of water? And a time, that's good. Thank you. Let's do a small. Right, okay, so we're going to go a bit on what has happened so far. We're going to go a bit in layers. So we're going to start from, you know, like the bottom, like the more mathy foundational layer, and we're going to go up and up and up. And a bit also like on a urgency layer, in the sense that the first things we're going to talk about, we have sort of solved them already, but the last things are still kind of open. So anyway, let's get started. So on the math layer, all the hash-based ZKVMs rely on a thing called proximity gaps, which is a very niche thing, and it basically, it's like math theorems on how error-correcting code words behave when you combine them, or even more interestingly, how error-correcting code, non-code words behave when you combine them. Like, you don't want to take two non-code words and combine them and get another code word. I mean, it's very niche, and I'm not going to get into it, but these sort of theorems are extremely important, and it's basically what this whole ZKVM thing is based on. And the theorems that sort of define how these things behave were introduced a few years back in some extremely prolific papers. But then, you know, there was like a theorem, and then next to the theorem, there was like, you know, there was like, oh, it behaves like this, and this is a security proof of how it behaves. And then next to it was like a conjecture that said, we cannot prove this, but it probably behaves also like this, and we're gonna use this conjecture as our security of our system, because by using this conjecture, you get lots of security for free. So, you know, like a system that is 60 bits of security on the provable theorem side can be 100 bits of security on the conjecture side. So, you know, people started using these conjectures, and when one person uses this conjecture, all the other people are forced to use this conjecture due to the industry being competitive. So we ended up in a situation where last year projects were offering, you know, like 80, 90, 100 bits of conjectured security. And this was all fun and games until, you know, like one paper came out that started digging hole into the conjecture, then another one came out, then another one came out, then another one came out. And, you know, like basically at the end of last year, essentially the conjectures were attacked so hard that it was extremely hard to rely on them, and they're still getting attacked. Like there's a few more papers I could stack on top of this, but essentially I think one stance we took in the beginning of this year was to sort of only look at provable security, which is what you can prove, the theorems, and this stuff. So this was sort of the beginning of this security sprint journey to focus only on provable security. Right, so that's for the math. Now, on the sort of a bit above, like on the proof system layer, on the protocols. So when you look at ZKVMs, and you know, they say, oh, we have this security, we have that security, and you see how they compute that security level. Each ZKVM has its own way of computing it. They have their own soundness calculator. One is written in Rust, the other is written in Python, the other is like some section on the README. Like, you know, like every project is computing security differently, and that made it very, very hard to compare apples to apples. And we had to compare apples to apples when it comes to L1 stuff, because like, you know, we're a neutral base, and we need to see, like, we had to be able to compare projects. So what we did naturally is make our own soundness calculator, which is universal, and, you know, like, you can plug any ZKVM into it and get the soundness of that ZKVM. And so it's called SoundCalc. You can find it on GitHub, and then it outputs a table like this that I have not made nicer. Sorry about that. But basically, you know, it has the ZKVMs in the left, and then how many bits of security and expected proof size. And it sort of, it might not seem like it by looking at this, but it sort of makes it easier to compare things and to get a better idea of where things stand. Yeah, so that's another thing that happened in the beginning of this year. And we're sort of in a good position right now. Now let's go into things that we're in a less of a good position. There is this thing called Poseidon. It's a hash function that is very nice to be used in recursive contexts, and ZKVMs are recursive contexts. All the ZKVMs use recursion, and if you use recursion, you want to have a hash function that works well with recursion, and Poseidon is one of them. And the EF has launched the Poseidon initiative a few years ago, which basically gives grants and bounties for people to attack Poseidon. And people did attack Poseidon. And now people, especially this paper from ETH Zurich, they broke Poseidon in some way. Like, they didn't break it exactly in the sense that the security level did not change, but still some fresh attack vectors were found in Poseidon that Antonio talked about earlier today, and it basically made us more distrustful of Poseidon. So now the question is how to think about this, how to think about Poseidon going forward. We don't have excellent answers for this yet, but we do have ideas. And yeah, that's another thing that happened this year. And finally, going to the sort of like top layer of architecture, when you think about ZKVMs, this is sort of how things look like. Like, you have a recursive architecture. In the bottom layer, you have all these small proofs that you have like a huge statement, you chunk it, you take small proofs, you recurse them, you get smaller proofs, and then sort of in the top of the thingy, you get like one tiny proof that corresponds to the entire execution. This is like a classic ZKVM architecture. And this is nice, but like when you start digging more into it, you see that, like, you know, this nice thingy is actually much more complex. There is like, between these nice boxes, there is abstraction leaks between them. There is global memory arguments. There is global things going on. You know, projects that are using hash-based snarks also use an elliptic curve argument to do global memory checks, or other projects that are hash-based, they use lattices as sub-protocols. And this is very hard to understand, like very hard to illuminate and to sort of map out when you're investigating a ZKVM, because these are like very tiny details that might matter in security. So this inherent complexity of ZKVMs is what we've been trying to tackle this year. And one way we think is a good way to tackle it is to sort of provide the framework that allows teams to formally prove the security of their ZKVM, of this entire thing. Like, we humans are pretty good at proving the security of these boxes, the individual boxes, but not yet that good at proving the security of this entire thing for many reasons. So we hope that by the end of this year, we provide a framework where teams can use to get a more overarching security proof of the entire thing. How are we doing this? Plenty of time. Okay. Okay. Right. Okay, so these are sort of the things that are happening on the various layers and has happened in the past months. And like, sort of looking forward in the rest of this year, given the goals we have, is, to start with a positive sentiment, one thing is that we know that 128-bit security is achievable, and it's achievable with a reasonable proof size. We know that because there is projects like Zisk that have gotten to 128-bit security already by using a very granular recursive architecture and by hardcore optimizing the heaviest circuit. So we know there is ways to do it. We also know that other projects can do it using a multilinear proof system where, you know, like you have a big table, and instead of treating each column separately, which adds lots of proof size, you sort of do like a multilinear trick where you consider it as a huge column, and then you can still argue about the individual columns. Anyway, like, there is techniques that we know of that can get to 128-bit security in a nice way. And this is a positive thing for us. And also, we have like various research leads going forward that we would like to explore more. For example, lattice-based proof systems are getting more and more powerful. It would be interesting to see how hash-based proof systems combine with lattice-based proof systems. Hash-based proof systems are very fast, but lattice-based proof systems are smaller, so maybe there is a nice combination that we could see there. Another thing is binary field proof systems used to be very exciting. I think they can still be very exciting. And not only that, but also projects that use binary field proof systems can also prove traditional hash functions efficiently, and this allows us to potentially use them to move away from Poseidon or from algebraic hash functions and use like a SHA-2 or Blake. So, these are potential avenues in the future for solving some of our problems. So, yeah, like closing up, I think we have a good path for the rest of the year, and also definitely interesting research directions to continue moving forward. And yeah, thank you very much, and happy to take questions.
Any questions? Here
we go. When you say 128-bit security, is that referring, so in your table, for example, to 128-bit classical security? Or is it in the QROM or?
No, it's on classical security.
I thought so, yeah, because when I looked at the SDocs paper, it had no analysis of the post-quantum concrete security at all. So do you think 128-bit post-quantum security is necessary?
Yeah, that's something that I don't have a good answer yet. I mean, it's even more interesting because the sound calc table I showed is showing security of the interactive protocol, not even compiled into non-interactive yet. So it's still hiding a few more details that we need to decide as a community how to handle. It's hard to say about the post-quantum security bits.
Yeah, my intuition is don't cheat on this, because...
Right. Yeah.
More questions? No, very clear. Thank you very much, George.
Thank you.
So we'll now break again and resume at 3:30 with some lightning talks. Thanks. What do you mean?
Well, thanks a lot, Rachel. Really happy to be here with you. And this is a collaboration between Aligned Lambda class and our amazing partners from 3MI Labs, who have been helping us developing the design and everything. So the idea is not to talk precisely of like some cryptography part, but mostly behind what is behind the design philosophy and why we need yet another ZKVM, because there are many. But we see that there are like some problems in the space related to them. And so we wanted to address this using the same philosophy we used in other places. So basically, what we think is that our application is going to be okay because we coded whatever we did, and then we assume that the rest is going to be okay and there will be no problems. And if you've seen lately, there have been a lot of attacks due to, for example, supply chain attacks, or because one of the dependencies you had some kind of flaw, or somebody introduced like some bug. And the thing is that if you look at the code bases of most ZKVMs, they are hundreds of thousands of lines of code. And even though like you have like nice security arguments and everything, one thing is what you have in paper and another thing is what you have built. And so the problem is that any of these things can fail, and you see that you have a very big attack surface, big assumptions, and then auditing these becomes really painful. So there are like three things that we see that keep happening. One is that you don't own your own stack. You depend on a lot of things that others built. And then, for example, they may introduce like a subtle bug, and that's outside your area of control. Then a lot of people generally create a lot of like abstractions, unnecessary abstractions, and that makes things very hard to reason about, and it doesn't make your code more maintainable or simpler to understand. It makes it, on the other hand, really complicated. And then, of course, the problem is that if your code base is really large, then nobody can read it all, reason about it, understand the different dependencies. And these are not bugs per se, but they are, I think, perhaps like poor engineering choices because they make your system really, really fragile. So we betted here on the opposite. The idea is that most ZKVMs got really performant by adding a lot of like clever tricks and a lot of optimizations. Here what we said is we are going to do the opposite. We are going to make something that is like really simple, has a very minimalistic code base, and it is performant. So what we are going to do is stand with one ISA. We are going to use one lookup argument, one memory model, so that our VM is really simple to understand and the code base is really easy to audit. And this is the same philosophy we use with Ethrex, which is the execution client developed by Lambda class, where you have the whole client in around 60,000 lines of code. And so that is something that is really easy. In fact, we wanted to make it even smaller. The idea is to optimize a lot. And we think that in this era where people like vibe coding, having something that is really simple is the way to go. It's really easy to write code, vibe coding, but that makes everything like really, really big, and then it hides a lot of subtle bugs. And we are going to see more exploits, not less, due to vibe coding. So as I mentioned, the idea is that we are following the same philosophy. The idea was that with the execution layer, you can read everything. You have everything vertically integrated. We use Rust. We use few generics. We think that you achieve performance through clarity, and we focus on long-term maintainability, which is something that some projects don't take into account. And the idea here with the ZKVM is more or less the same. The idea is that all the crypto primitives will be precisely in the code of the VM. We have exactly one language, Rust. The idea is 3MI Labs developed a very nice spec that we are currently optimizing, and the code maps one-to-one to the spec. And the idea is that all this makes it really easy for the code to be formally verified, which is one of the requirements the EF is putting forward and is spending a lot of money to ensure that we don't have any bugs. So to give you an idea of the architecture, or at least the structure of the VM, the idea is that we have 14 tables, more or less, 18 chips and templates. The idea is that we have the general CPU chip that dispatches to the rest, and this makes it very easy to reason about what's going on with the VM. And then the idea is that, as in the rest of the VMs, we have a memory argument that unifies everything. And the idea is that the spec is really clear, and we know exactly which kinds of variables we are using in each case. So the idea is that most of the constraints are simply reusable. So we have what we call templates. And the idea is that we have bit templates, sign, also addition and subtraction are inlined for performance, negation, and of course we have the decode table, but that's mostly a lookup. And the idea is that it's really easy to compose the different things. As for the chips, we have some related to control and instruction fetching and decoding. Then we have all the part related to arithmetic, then to memory. And of course, then we can extend everything to make it more efficient by adding specialized coprocessors. And the idea is that we work everything on a log-up bus. And in general, the signatures are pretty small, and we keep just one running sum. We don't have complexities, for example, related from having local lookups and global lookups. And the idea behind the proof system is go really easy. So we are going to use a 64-bit field, in this case Goldilocks, using a cubic extension so that we can really target 128 bits of security. We are using Fry because it's really well understood. There are a lot of efforts at formally verifying it. For the time being, we are going for qedb as the hash function. Then we are going to see if it makes sense to use an algebraic hash function, or we could use, for example, Blake. The idea with the lookup is precisely use logup, and then for the memory, it's like a standard offline check. And the idea is that, sorry, it says conjectured, it's provable. So the idea is to have 128 bits of provable security. Then, of course, for the memory and everything, the idea is that we can do this in the offline check, and so we will carry information about the address, the value, the timestamp, and since registers are accessed pretty often, the idea is to have a special way to deal with registers that is simply an optimization. And then what we are going to ensure is precisely that when we read a position and then we write, there is an increase in the timestamps. We still have to think a bit more about recursion. We are also thinking about using a streaming prover, and we still have to give some thought, but the idea is to use something simple. Some people use, for example, elliptic curves to try to simplify some of these things. We want everything to be, of course, post-quantum secure. So we are not going to use any type of strategy. And the idea is that the current state, which, for example, can prove Ethereum blocks using Ethrex, is only 27,000 lines of code. That is like pretty simple. The idea is to go less than that, but in the end, I think we will end around 35 or so. And the idea is that we also have like minimal dependencies, and that way we can control what we have. So we are not publishing numbers yet, but the idea and the numbers, preliminary numbers that we have is really good. We are close to, in performance, to many of the state-of-the-art VMs. We hope to optimize the design a little bit more before we release it. And the idea is that right now we are on this version. We have to add like some few coprocessors to make it like faster to verify Ethereum blocks, adjust the security. And then we are also right now working on the GPU version. So the idea is to have the GPU version in the coming weeks. And then we are analyzing some alternatives, maybe adding log-up GKR. From the performance point of view, it doesn't change much in terms of memory use. It's really good. Then we have to see some strategies to maybe shrink proof sizes. And of course, the Ethrex integration is done. We have to still improve some parts, but it's working. And so we have a full stack with minimal dependencies. And well, this is just the idea to proving Ethereum blocks in real time. And so we are using Ethrex. With that, we get the RISC-V 64 IM-ELF, and then we run that on top of the Lambda VM. We generate the Stark proof. The idea is to compress it so that it can be then verified in the L1. And so, well, the idea is that we want to make this VM as minimalistic as possible. We take into account every line of code. We try to have as few generic parameters as possible, as few dependencies as possible, and as always, try to keep a 1-to-1 spec-to-code constraint ratio so that it is easy to audit and formally verify. And so the idea is this is not a new philosophy. We are doing what we did with the execution client. The idea is this is going to be open source. We plan on releasing really soon once we finish some optimizations and checking the spec and everything. And the idea is that a reviewer can easily read everything in a whole week. And the idea is to precisely make these small enough to formally verify and to prove Ethereum. So if you want to learn more, you can come and talk to us. And if you obviously have questions related to cryptography, you can also ask our guys from 3MI Labs, who are amazing. Thanks a lot for everything.
Amazing. Thank you very much. As Diego said, if you've got questions, come and find him afterwards. We'll swap over. Thank you very much. Okay, so next up, we have Roman Volk from Tachyon presenting Mercy's private token transfers via MPC and co-snarks. We'll just wait for your slides to catch up with us, and then we'll get going. I did rattle that off quite quickly, to be fair. Yep, brilliant.
That is too far. Great. Hi guys, thank you for the introduction. Yeah, let's jump right into it. And the title, we say we're using MPC and collaborative snarks. So I want to quickly spend one slide on introducing what this actually is. So MPC, or secure multi-party computation, is a cryptographic technique that allows us to compute functions on private data without leaking this data. And the way it works is that we have a set of compute nodes. So here on this picture on the right, we have 3 compute nodes, and they get so-called secret shares of the data. You can see these random looking noisy images there. And these secret shares do not leak anything about the underlying data itself, but the MPC nodes can use them to compute functions on them. And this might require some communication, but also this communication between the nodes does not leak anything about the data. And what the outcome of that is another set of secret shares. And once the MPC nodes are done with computation, they just combine these secret shares and get the desired result. So here it is supercat. And that's the way we can use MPC to compute on encrypted data. Regarding collaborative snarks, that is essentially, simply put, just creating a zero knowledge proof in MPC. So we have the witness as secret shares, and we compute the proof in MPC, and yeah, essentially a collaborative snark. So by having MPC and collaborative snarks, what we get is the compatibility from MPC, provability from the snark, and from both techniques, we do not leak anything about the underlying data. So coming back to MERSes, the actual goal of MERSes is that we want to write a private wrapper around any token. This could be a native token like ETH, it could be USDC or any other ERC20 token, and we want to be able to deploy this wrapper on any EVM compatible chain. And what this wrapper should be able to do is that on one hand, if a user has some balance with this wrapper token, we do not want to leak anything about this balance of the users. Also, when a user wants to make a transfer to someone else, we want to be able to hide both the sender and the receiver, but also the actual transfer amount that the user was sending to someone else. And the way we achieve this is something that we in general call private shared state, and the blueprint for that is actually quite simple. So on-chain in our wrapper contract, we only have a commitment, a cryptographic commitment to all the balances of the users. The balances themselves are stored off-chain on an MPC network in secret shared form. And since they are secret shared, the MPC nodes can compute on them. For example, when I make a transfer, then the MPC network can update the balances of the users. This will also compute a new commitment of these balances, which we then store on-chain to reflect a new state. And the smart contract will only accept this new commitment if we also provide the zero knowledge proof that the computations were done correctly and as intended. And this is where the collaborative snark comes into play. So summarizing, on-chain we only have a commitment, and we store the actual balances in some data structure off-chain in an MPC network in secret shared form. So how do we achieve a private and provable smart contract there? So on the MPC network, what we actually want to build is some kind of hash map where we map a user address to some kind of balance. And here, these square brackets, they indicate already, these should be remain private. So the balances are stored in secret shared form, but also when we access these balances, we should hide which addresses we are actually accessing here. And our way to achieve this is essentially we model this hash map as a Merkle tree, and then this Merkle tree is fully secret shared on the MPC network. On the leaf layer, we have the actual balances of the users, and the path from the commitment to a balance is the address of the user. And the root node of this Merkle tree is just a commitment to the whole data structure, which will be public on-chain. And whenever we update the balances, we also update this root commitment here, and this is the new commitment that we store on-chain. And we can use membership proofs to prove that the updates of all these leaves were done correctly. So far, there's nothing too special about this, but what is interesting about our design is that each layer of this Merkle tree is implemented as a so-called oblivious RAM. And that is a primitive from MPC, which allows us to read and write to these slots without the MPC network actually knowing to which slots it actually accessed. So the MPC network will just get secret shares to the addresses we want to access here, and the oblivious RAM primitive allows us to read these slots and update these slots again. So from the point of view of the MPC network, when a user wants to do a transfer, a private transfer, what is actually happening is that the MPC network will get secret shares from the transfer amount, secret shares from the sender address, and secret shares from the receiver address. And it also requires some kind of user authentication here, because we don't want to give anyone the possibility to make transfers on behalf of someone else. So the user needs to also provide a zero knowledge proof that it knows the secret key corresponding to the sender address here. And if the MPC network is able to verify the proof, what it does is essentially just accessing the oblivious RAMs in the leaf layer, modifying the balances. This also triggers then update of the whole Merkle tree structure, produces a new commitment, and this is the commitment that we post on chain. The MPC network, as we said before, also needs to create a collaborative snark, and this essentially just proves three things. On one hand, the balance was positive. On the other hand, the sender needs to have enough balance to fulfill the request. And the third thing is that data structure needs to be updated correctly, and that essentially requires 4 Merkle proofs, 2 binding the old balances to the old commitment, and 2 using the same paths to Merkle proofs, which prove that the new balances produce the new commitment that we stored then on chain. So this is essentially everything that is happening on the MPC side. And with that, we could already implement full private transfers. However, if we just follow it the way I talked about now, we will get a very inefficient design. And the reason for that is that in Ethereum, we usually have 160-bit addresses. And if we build a Merkle tree that has the addresses as the path from the commitment to the balances, then we need 160 layers there. In our design, where we have ORAMs for each layer, this also implies that we have 160 ORAMs, 160 ORAM accesses for each transfer, and also in the lowest layer we have 2 to the power of 160 elements in there. And this is way too big for any ORAM design to be efficient at all. So we need to come up with some kind of optimization. So we experimented in the past already with some sparse Merkle tree designs in MPC, but what we learned in the last months is that the most efficient solution, in our opinion, is to introduce something that is called an ID registry. And that is essentially when a user wants to engage with our private token transfer system, it has to register in this ID registry. And this is essentially then just a lookup from the user address to some incrementing index. So if I'm the 7th user to register, I get the index 7. And this is then the index that we use in the Merkle tree on the MPC side to access the balance of the user. And essentially, when a user then wants to make a private transfer, the authentication proof also needs to take account this lookup from this address to the index. So how did we implement this ID registry? Essentially, this is also just a Merkle tree. You see this here on the left side. This is a fully public Merkle tree, and when I register, then I get the next free leaf assigned, and the bar from the commitment to the leaf will be my index. That is also the index on the MPC network. So here on the right is the MPC Merkle tree, and you can see that the path is the same as in this public ID registry Merkle tree here. So as I said before, when the client wants to authenticate itself with the knowledge proof that it knows the secret key to address, we also now need to include a membership proof of this ID registry Merkle tree, and then that the path for this where my public key is stored is then the one that is put into the MPC network as a sender index. Okay. Sorry, yeah. So this is now the full view of the protocol from the point of view of the client. So when I'm a client and I want to engage in a private transfer with Merces, first I obviously need to register with the ID registry. If I have already done that, then I still need to engage with the ID registry to be able to create this authentication zero knowledge proof. Then I secret share the amount that I want to send to someone else. I secret share my index. I secret share the receiver index. And what I also need to do is create some commitments to sender ID, receiver ID, and the amount. And these commitments will then later be used to bind the proof created by the MPC network to my user intent. Also in our system, we give the secret shares to the MPC network via the smart contract. So what we do there is we encrypt each secret share with the public key of the receiving party, and that is also posted on chain. And the client then creates a zero knowledge proof that proves everything of that. So on one hand, the ID registry lookup, that it knows the secret key for its address, and also that the commitments and the encryptions of the secret shares were computed correctly. Once this is done, it posts this into our wrapper smart contract, where the zero knowledge proof gets verified, and on success, the request gets put into some action queue, and the MPC network regularly queries this action queue, reads the ciphertext from chain, gets the secret shares from it, and is able to update the full Merkle tree based on these secret shares. Once it's done, it creates the new commitment to the data structure and the zero knowledge proof, proving that everything was done correctly. Okay, regarding performance, on this slide I give you some benchmarks on the MPC networks computation. This includes reading and updating the data structure, and also creating the zero knowledge proofs in MPC. And I give you numbers for different sizes of the Merkle trees, so how different users who are registered in there, and also for different machine setups. So on one hand, we have a M7A 4x large, is a fairly standard AWS CPU machine. And on the other hand, I give you benchmarks for a G5 4x large, where each party also has access to a graphic card. And you can see if we have around 100,000 users registered in Merses 2, it takes around 200 milliseconds to process a request, including zero knowledge proofs. And this is on both on the CPU and the GPU machine. If we have around 4 million users registered in Merses, then on the CPU machine, this you can see it takes a little bit longer now, around 1 second for this request. But on the machine with access to a GPU, we see that the scaling is way better, and here it takes roughly 370 milliseconds to fulfill the request. So in total, we get around 3 to 5 transfers per second on the MPC side, depending on how many users are registered in the system. Okay, this brings me already to the end of the talk. I introduced Merses, our solution to realize private token transfers. We hide sender, receiver, balances, and transfer amounts. And I want to say that we use MPC for privacy, but for integrity of the whole system, we only use the ZK system. So essentially, if all the MPC parties would collude, they would not be able to misuse the funds. So, and we implemented this design using what we call an oblivious hash map, and this is based on a Merkle tree and ORAMs. The design is fully implemented, and then if you scan this QR code here, you can interact with a demo that we launched on a Plasma testnet, so you can make private transfers there, and also see what is actually posted on chain, and you will see that nothing is actually leaked to the users. Throughput of our system depends on how many users are registered for Merses, and it's around 4 TPS. And I want to note here that if we deploy a system where we always allow to leak sender and receiver, then we can actually get up to 300 TPS. And for this system with the relaxed security assumption, we actually wrote a paper that we published last week, and there we have a full UC security proof in there. So future work about our system. So on one hand, so we also hint this in this demo already, is that we want to be able to implement some private swaps. So when you have deployed some tokens into our Merses system, you can swap this to some yield-bearing tokens, for example, from Aave or Morpho. Then your deployed tokens actually generate some yield. And another thing is we want to integrate Merses as the payment backends from some more complex protocols, for example, the X402 payment standard. That's the end of my talk. If you have any questions, I don't know if you have time, you can ask them now or find me later, and then I will be happy to discuss further. Thank you for your attention.
Wonderful. Thank you very much. And that was truly a lot of information in 15 minutes, so well done. That was a true lightning talk. Okay, so next up we have George Weiss from Pada Labs, and he will be presenting non-deterministic auto-precompiles. Again, if we have time for questions in this slot, we can ask them. If not, you can find George afterwards. Okay.
Nice. Good afternoon. Yeah, I want to give an update on some of the new ideas that we have for auto-precompiles. So let's jump right in. What is an auto-precompile? It's a ZKVM precompile, so it's something that makes ZKVMs faster. But it's not written by us or by an AI or anyone. It's automatically generated from a specific guest program. So you can think about, you have a ZKVM, you have some guest program that you care about. You give that to us, and we give you a faster ZKVM for this specific program. So let's dive into how this is done concretely, and then I can talk about some of the new ideas. So for the purpose of this talk, you can think of a ZKVM as just some collection of ZK circuits. So for example, you could have a RISC-V ZKVM that has a circuit for each of the RISC-V instructions. You could also have fewer circuits. An extreme example of this being Jolt, that has just one circuit. Doesn't really matter. And then you have the guest program, which is a list of assembly instructions. And so the first thing that we do to the program is we segment it into basic blocks, which means that we only look at consecutive instructions where only the last instruction can be a branching instruction. And then the goal is to make a new circuit that can prove execution of the entire basic block in one go, as opposed to proving instruction by instruction, which is what a ZKVM would normally do. And we start out by doing the most obvious thing, which is copy-paste together a bunch of circuits that the ZKVM would have used if it would have proven this basic block. And we wire it up correctly, and we have a new monolithic circuit that can prove execution of the entire basic block. But of course, that would be useless if we wouldn't then optimize it and get a smaller circuit to do the same work. So let's dive deeper into how these optimizations work. Actually, no. This is a summary slide. So right now what we see is that for a typical basic block that we get from compiling Rust to RISC-V, we see about a 3 to 4x improvement in efficiency in that optimization step. That's like kind of the average case. And then in some cases, we see a higher efficiency, for example, like more than 10x on Ketchup. Yeah, exactly. It's RISC-V compiled to, I think, OpenVM in this case, and then applying this optimization. So let's look into more detail. Here I'm just presenting like a single instruction, so forget about basic blocks. This is to keep this really simple. And this instruction is incrementing one register. So think about a Rust program that has some kind of loop, and you have a loop counter that you need to increment each iteration of a loop, which is stored in register 29. And so we want to prove that increment. So typical ZKVM would commit to a bunch of data to prove correct execution of this instruction. For example, the current program counter, the current time step, then the instruction data, which is basically encoding stuff about the instruction, like what are the source and destination registers, what are the immediate values, stuff like this. Then there's 2 operands and a result, which are both machine words. And in this example, they would be 32-bit machine words represented as 4 fiat elements, each of them encoding 1 byte of the 32-bit word. And last but not least, there's some auxiliary data needed for the memory argument to prove that all the register accesses have been done correctly. And already today, we can remove most of this because we're building a circuit for this very specific instruction, so we already know the program counter. So we don't have to commit to it at runtime, we can just hard code it in the circuit. Similarly, we can remove the instruction data because it's implied by the program counter. For example, in this case, we know that the register being accessed is register 29. We can also remove the second operand in this case because it's an immediate value. And we can also remove most of the memory argument auxiliary data because in general, an addition instruction would have the infrastructure to access up to 3 registers. But in this example, there's only 1 register being accessed, so we can remove 2/3 basically. So that's the state today. We get like a smaller circuit. And let's have a look into like an even more concrete example and check the case where the loop counter is 42. So we want to increment register 29, which stores 42, we get 43. So we would commit to the operand and to the results. And And in this case, 42 and 43 are relatively small numbers. So the 3 first bytes of the representation will be 0. But now imagine this loop never runs more than 255 times, and it will always be 0. Of course, that's not something we might be able to prove, but we can still observe that this is the case typically. So the observation here is that even in the very optimized case, we still have situations where many of the trace cells that the prover still commits to are either equal to each other or equal to a constant. In this case, they're equal to a constant, but even if the loop counter was very big, the chance that the most significant byte changes when you increment by 1 is pretty low. Like, it won't be the case for most inputs. So the idea here is, let's build a precompile for the typical case, kind of losing completeness. So we get a circuit that only has a satisfiable witness in the typical case, but is smaller to prove, and the prover needs to have some kind of fallback to the like for situations where it doesn't apply. So in this case, if the loop counter becomes too large, the prover needs to fall back to something else. This could be another auto-precompile, or it could just be falling back to the circuits that the ZKVM already has. Because already today, prover is not forced to use an auto-precompile. It can kind of non-deterministically choose the circuits that it uses to prove the statement. So yeah, that's what we call an optimistic precompile. It's built in 3 steps. We first run the program on a bunch of representative inputs to collect data. Like I mentioned, we check for trace cells that are usually equal to each other or usually equal to a constant. And then, when we're building the circuit, we over-constrain it. So whatever observation we made in the first step, we add that as a constraint, and that basically enforces that observation, and the circuit will not have a satisfying witness if the observation, like if the condition doesn't hold. And then we just pass this to the existing optimizer, which will just do the right thing. So for example, if it sees a circuit where 2 variables are constrained to be equal, we just allocate a single variable and get a smaller circuit. We implemented this on OpenVM. It's a prototype, but we tested it on a program that verifies Ethereum blocks. Looking only at the part that's not accelerated, because OpenVMs comes with precompiles for something like Ketchup, but it also still needs to prove a lot of RISC-V stuff, so we're only looking at that part. And then we're kind of assuming that we can accelerate all the basic blocks. And by doing that, we get this first number, this 3.3x, without optimistic precompiles. And with optimistic precompiles, this number goes up to 4.8x. So we can reduce the amount of data that the prover has to commit to by this factor. And so compared to the current state, it's like a 1.5x increase in efficiency. So that wraps up optimistic precompiles. I want to briefly talk about a very related idea, which is branch prediction. So consider this example. So here, the program does division, but it also does some error handling and checks whether the divisor is 0, and then if not, it carries out the division. But probably most people are not going to attempt to divide something by 0. So the typical case will be that there will be 2 basic blocks that are executed one after the other. The first one checks whether the divisor is 0 and then does a conditional jump, which would typically jump to the second block, which carries out the division and does the function return. But the same principle applies as for optimistic precompiles. We can just build a precompile for the typical case. So in this case, we would build a precompile for the super block, which would just prove both basic blocks in one go. And so the way we build the circuit is basically returning the conditional jump into an assertion. It won't be able there will not be a satisfying witness if the condition doesn't hold. So the circuit would still check that the divisor is non-zero. But if it happens to be 0, then the prover just won't be able to use the circuit and has to fall back to something else. And the motivation for branch prediction is kind of this chart. So here we looked at the relationship between the number of cycles that were proven in one auto-precompile and the effectiveness, which is this number that I was presenting before. And right now we see that many basic blocks have about 10 instructions in them. And we get a 3.3x effectiveness. And we're hoping that with branch prediction, we can bring this number up, kind of move to the right side of the chart. I also included the number of the far right here, which of course is not realistic. But I thought it's kind of interesting because at this point we're kind of approaching having a single circuit to prove the entire computation. So branch prediction can get us in that direction. So that's it. To summarize, I presented two ideas, optimistic precompiles and branch prediction. Both of them were expecting to give us very significant reduction in trace cells. And the unifying theme here is that what we're doing here is exploiting the non-determinism of ZKVMs to be able to optimize for typical situations.
Okay, great. We'll move on to questions, if that's okay.
Does this kind of technique mean that you can transfer other kinds of optimizations from conventional processes like caching, for example? So if you're doing a memory access, you probably know that it's within a small subset of the memory, so you can be optimistic about that as well.
That it's like you're like caching pages of memory.
Well, it wouldn't necessarily have to work in the same way as a cache and a processor, because you can just basically guess that the memory location is one of a small number of possibilities, and then that's your optimistic recompile. So you don't need to actually keep track of the same cache information that a processor would be doing, but you get the similar effect.
Yeah, I think we've seen something like this. That, for example, some of the things that it can observe is that it will know more exact, for example, the most significant limb of the memory address, which I think is what you're referring to. What we've also seen is that as part of a memory argument, you need to commit to like a previous timestamp or the difference to the current timestamp, which is often a constant. Because if you're accessing something in a loop, it's always like a difference in timestamp will always be the same. So that's something we've seen in practice.
We've got two more. We'll take both these questions if you want to go ahead, and then we'll come to you, Tobias, afterwards.
Yeah, I just wanted to say that basically if you have a predictable memory pattern, a memory access pattern, you can, or at least like optimistically, like predictable memory access pattern, using sparsity-based arguments, you can sort of turn it into a single vectorized access in a sense. So this is one way of doing this.
Great. Okay, we'll take this final question and then we'll move on. We should have Maddie here ready for next time.
Yeah, so the question is, have you considered loop unrolling? I guess it's kind of related to branch prediction, but that means if you have like a loop, maybe you do 256 iterations of that loop as the precompile, and then you can reuse that.
Yeah, I would say that loop unrolling is a special case of branch prediction. So I think it's just captured by this.
Yeah, that makes sense.
Thanks for the many questions.
Thank you very much. Okay, so this is our last lightning talk of the day. Then we'll have break. We'll have one more 30-minute talk, and then it'll be the panel for the end of the day, just so everyone's aware. Okay, so next up, we have Maddie Sedegat from Soundness Labs and Ku Leuven presenting proof-of-seed ZK-based quantum migration without address changes. Take it away.
Thank you so much for the introduction, and good afternoon, everyone. I hope that the online version and not the PDF one, because I have some animations that I'm using. I hope that it's going to work. So in this talk, I'm going to cover the result that we had and presented a couple of months ago at Financial Crypto, which is a collaboration with folks at Mist and Labs. And the question that we want to answer in this presentation is that, is it possible to use the ZK proof that you already got a lot of insight today with multiple amazing talks to seamlessly migrate to post-quantum world? If this is possible or not, I'm going to answer. You already have the context. This is the good news. I know that this is the end of the day and you already had a very intense day. It's not like a super new topic. There was multiple episodes at ZK Podcast that was discussing this topic before. And funny enough, last night that I wanted to go to bed, I just refreshed my podcast application that I have on my phone, and episode 400 was exactly the topic that I wanted to present, and it forced me to change 2 of my slides and also remove 1 of those. Fully recommended, by the way. So many people might ask that how quantum computer is going to show itself in the blockchain space. For those of the people who are not believing to these breakthroughs or advances that is happening, I'm not the right person to answer a timeline, but imagine that the first time that is going to the Satoshi coins are going to be touched, this is a situation that we should expect from the market impact. And there is also another important aspect that we have to consider. There are a lot of dormant accounts that the users are going to lose the migration calls, and it's very hard to expect the users to take an action for changing their legacy systems to the post-quantum secure ones. And another problem for this space is that if you want to compare it with another spaces in the internet that they are being affected similarly to blockchain in the terms of quantum threats, is we would like to keep the addresses unchanged if that's possible. So a quick reminder about how the blockchain works with the focus on Ethereum itself. Whenever a user joins to this network, they will get a key pair, which is a signing key and also public key. And the address is being defined through hashing the public key and some specific part of the output. And whenever you want to sign and make a transaction, you need to use the signing key and essentially sign the transaction details for the integrity purposes. And this is going to be submitted to the mempool. So the validators need to know your public key to check the validity of the signature. And if everything is fine, then essentially they are going to agree on the validity of the block, and the block is going to be created. I already highlighted in red, there are 2 parts that the signature is being used. The first one is an execution layer that the user is trying to make a transaction, and the second part is in the consensus part that the signature is being used. Another thing that I want to highlight in this slide is that the public key is going to remain hidden and is going to be behind a hash function as long as you are not making a transaction. Okay, so once you make a transaction, you need to reveal your public key, and once your public key is revealed, then there is a possibility for a quantum computer who has a sufficient number of logical qubits to get your signing key. And let's draw a map that how does it look like. So as I said before, the digital signatures for the execution layer that mostly are being ECDSA and EDDSA are going to be directly impacted by this threat. And for the consensus part, which is the BLS being used in the proof of stake protocols, is also directly being impacted. So in the first threat, the transactions are going to be forged by the quantum adversary. And the second case, which is less probable from the other one, because we have to expect that the quantum adversary is rational. They already solved a super complex problem, and they are not going to do a rookie mistake whenever they are going to do that. Is going to be the proof of stake attack. By the way, quantum computer is not going to do everything better than the classical computer except these 2 algorithms, the Shor algorithm and the Grover algorithm. And the rest of the things are going to be either partially impacted or they are going to be secure. The symmetric cryptography and also the hash functions are not going to be impacted. So because of this, we are just going to focus on the execution layer. And as you know, that Ethereum is also working great on bringing this, replacing these PLS signatures with XMSS and also using the LinVM to aggregate the hash-based signatures. So the naive approach for this would be let's switch to the post-quantum signatures. We have some candidates here that was standardized by NIST, like Falcon, like SNCS, and also so on. But the problem is that once you change your signing key, it means that the public key is going to be changed and the hash of the public key is going to be changed, okay? This is natural. And our goal is that how we can use the backward compatibility feature in the legacy systems to keep the address and also not move the assets. Because there is also a front-running attack for the quantum adversary that whenever you are asking for the migration, they can actually do it faster than you, that you can refer to the Google paper for more details. So again, we would like to preserve the addresses, and also we would like to just take care of the exposed keys, and they are like a dormant accounts, and also protect this type of accounts. And also we would like to be like a key generation agnostic, which means that it doesn't matter that which type of account and wallet you are using. And another aspect is that most of the people would like to and prefer the hash-based constructions. There is a cons for this like a perspective that there is no algebraic property, and we are just losing some of these properties that we already had in the ECC-based constructions. So the core idea is quite simple. We have some modern chains like Solana, Sui, and others that they are based on EDDSA signatures, and we have also Bitcoin and Ethereum that they are based on ECDSA signatures. In the ECDSA, whenever you are creating an account, you are going to get a random signing key, and the signing key is going to give your public key, essentially, which is exponentiation in the group. But in the EDDSA, the key derivation mechanism and the path is slightly different. First of all, you pick your seed, and your seed goes to a hash function, which is SHA-512. It's exactly the key derivation mechanism referred to RFC 8032. Okay, so it is they are just following a standard. And the core question is that, can we use this seed that is protected by the hash function? Because we know that the Grover algorithm is just giving us a quadratic speedup for breaking the preimage of the hash function. Can we use this seed for post-quantum signing processes? And unfortunately, the signing key, because there is no like a path except like a BIP32 and BIP39 in the hardened and key path that I'm not going to describe in this talk, unfortunately, there is no chance. And once the quantum adversary having access to your public key, they can get the signing key, and then essentially they can impersonate you and somehow like drain the account. But in this case, we have some advantages in the EDDSA-based chains. The relation would look like this. That you have a message, that the message in a first step can be like a transaction details that we already signed using ECDSA or ADDSA, and you have also a public key, plus some extra information that is for binding purposes to make sure that there is no mix and match attack. And what this relation proves is that proving the knowledge of the seed and also the key derivation mechanism that reaches to the same public key, okay, that the signature is going to be verified based. What we expect from the proving system to prove this relation is, first of all, it should be post-quantum secure for sure. I mean, post-quantum soundness is more important than here, very critical for us, because the non-post-quantum one also provides us the post-quantum zero knowledge, by the way, because it's information theoretical zero knowledge. And we would like to have also client-side proving. Client-side proving is very important, otherwise you cannot like outsource your seed, which is the full control of your asset, to a server. It should be also memory efficient, because most of these wallets either are in the extension of the browser or they are in the mobile phones. It's not like a heavy like a machinery that we are expecting here. The proof can be also one time, because once you have the post-quantum signature being supported by the chain, you can only use this technique, this migration technique, for keeping your address the same, okay, for account or address consistency purposes. And instead of like putting the transaction details as a message for binding purposes, now you can use the public key of your post-quantum signature, and then essentially the network is going to check the validity of the signature and your transactions from that time onward based on that post-quantum public key. And this is going to be a one-time ZK proof, because on-chain verification for these post-quantum signatures is expensive, and we shouldn't expect it to happen per transaction if this is the situation that we are dealing with. By the way, very recently, Coinbase also had a report, and they already also discussed multiple strategies, how the migration would look like. And the second column is about this idea, that somehow like meet most of the conditions that they are just discussing and describing there. Another important thing is that it is somehow like a signature of knowledge. We need more than knowledge soundness. And this is simulation extractability because we don't want to do the malleability of the signatures because someone else can pick it and make it different. And there's also a common trick that put like a session ID to the Fiat-Shamir, and then essentially you can have this property somehow for free without expanding and increasing the proof size. How the benchmarks looks like, there is an open source code that you can follow here. And the circuit looks like this. The blue dash box in top is something that is happening outside the circuit, and the red box is inside the circuit. As you know that most of these client-side proving systems are based on ZK-friendly curves. BN254 or the other things. And unfortunately, the relation that we want to show is in ED25519, which is a legacy curve, and we don't have enough roots of unity. Okay? We need to do some emulation here. What we did initially was we somehow used 3 limbs for this. You know better than me. Then essentially we could come up with these numbers in Ligatron ZKVM. And this is what is that open source right now. And we could actually do it better using VRBase and LeanVM. Like an Easter egg that I left in this slide is that you can also use some decomposition technique because you don't need to just do everything in the single circuit because it doesn't necessarily that the hash relation is going to be the same as checking the consistency of the public key. By the way, the public key should be checked inside the circuit. There is no way. How does it look like? Okay, it seems that doesn't play. That's bad news. Okay, because this is a PDF version. I just left it as an urgent case, but it doesn't matter. I will post it on my homepage afterwards. So the demo is supposed to show you that how does it look like. I can just describe it. How does it look like? So essentially, you have a wallet, and the wallet is holding the seed. You can copy and paste it, and whenever you are making a transaction, you just press generate the proof, and the proof is supposed to be the second condition for the validity of the signature and the transaction. And it can be like an upgrade in the chain itself, and as long as if the quantum adversary is trying to drain your account, since it cannot provide the second condition, it's all the time rejected. But as you know, we don't have only the software wallets and the self-custody wallets. We have different type of wallets, HSM wallets, MPC wallets. In the HSM-based case, we don't even have the API to get the signing key, and we cannot expect to get the seed, okay? Because we need to generate the proof, and we cannot run the proof inside the HSM. Do you want to do it? Talk to these HSM providers. Good luck. After 6 years, they can say to you a big no, and this is not going to happen. And for MPC is also the case, because none of these MPC providers are following these standardized techniques, and everybody's doing whatever that they want. Is for marketing purposes or for different purposes that they just want to showcase that my scheme is secure than the others, and they are just doing different stuff. Okay, so we don't have any clean path for this type of accounts. How ZK can come to the rescue for different type of accounts? Because as I said before, the previous idea only works for EDDSA, which is a very small fraction of chains that they are supporting, and BIP39 and BIP32 for ECDSA. But we have also different type of accounts that doesn't work at all. This is the problem. You already, I think, heard about the anonymous credentials multiple times today in different talks. This is the immediate solution that we can assume. In the anonymous credential, someone is proving that they have access to a signature that is coming from an issuer. So as I said before, as long as you're not making a transaction, then your public key is going to remain secure, and you're not threatened by the quantum adversary. Okay, because the quantum adversary only has the hash of the public key, and from hash to public key is not possible. All the time prove that you have the knowledge of a signature for this transaction, and also show the consistency of the address with the public key that the signature is being verified inside the circuit. Okay, so you don't reveal anything on chain, and then essentially this is going to help us to do it on top of these other wallet types. Again, there's another demo that I cannot show you, but this is also more or less the same concept that you can connect to your MetaMask, that essentially you make a transaction, but you wrap it before sending on chain, and this is going to be a smart contract. It's some delegation technique that Ethereum does let you to do that. And we are actively working, and this is also another open source code that you can check it out. We are using Longflow ZK, developed by Google, and we are actively working with them to reduce the on-chain cost. As a conclusion and a wrap up, we already talked about like EDDSA chains, that they have like a structure and deterministic like a key derivation path that led us to wrap the signature using a post-quantum ZK proof. But unfortunately, it doesn't work for any cases. And also for MPC and HSM that we can actually use again ZK for this purpose by hiding your public key. We call it as a hidden public key, like a concept that essentially can be used. Again, I mean, refer to episode 399. Is the ZK dead? I don't think so, if it is my personal opinion. There are some new like terms and applications that we can see here. As you can see, it's like a post-quantum migration. There are a lot of traction and like discussion that is happening. Anchorage also had another idea that whenever you have a post-quantum signature, you can use the secret key of your legacy system on the condition that the public key wasn't revealed at all, for the key derivation mechanism of the post-quantum signature, okay? And then prove it inside the circuit. Again, good luck, because the key derivation mechanism for the post-quantum signatures is extremely heavy to be done inside the circuit. And there's another idea that to put a timestamp, because we know that at the moment there is no quantum adversary, then let's put some timestamp for your legacy system and prove inside the ZK and the circuit that you have something valid before the quantum adversary arrives, okay? Before the Q day. Yeah, this is the end of my talk, and happy to answer a question if you have time.
Yeah, thank you. Yeah, so we could maybe take one question, or to be honest, you can ask questions. We'll just be going into the break, so we can stay as long as you like. So we'll start with questions.
I just wanted to describe how a similar concept works in Zcash. So if you look at ZIP 2005, so we already derive the keys for our circuit deterministically in most cases. So we can use something that's kind of similar to the EDDSA approach. There's one exception, which is threshold signatures using Frost, but because those hadn't been widely deployed yet, we can specify the key generation for Frost, taking this into account, and so we can kind of provide an alternative that will work post-quantum. So the idea is that you might have to leak one of the keys from your hardware wallet, and also do a DL-based signature. There's another alternative which kind of uses a smaller circuit in the hardware wallet, and that works similar to one of the ideas from the slides. So basically, we've come to similar approaches from different directions.
Amazing.
Wonderful. Okay, so if we have any more points or questions to talk to Maddie about, please find him in the break. We're going to break for 30 minutes until 5. Then there'll be the final talk on this stage, and then we'll be moving on to the panel, which will be the end of the day. Okay, go and caffeinate, feed yourselves. Thank you, Maddie. panel. So next up, we've got Inokenti Sanofsky from Aztec Labs, presenting origin tags, dynamic detection of Fiat-Shamir bugs in complex systems. Take it away.
Hi, so my name is Inokenti. I'm head of security at Aztec Labs, and I'm going to talk about a mechanism that we've created to detect some of the vulnerabilities that often arise when we create Fiat-Shamir based systems. So let's dive in right away into most basic interactive protocol. Let's say we are trying to prove the knowledge of the discrete logarithm in some secure group. The way this usually happens is the prover generates some sort of secret random scalar car, then commits to it, sends it to the verifier, receives a challenge from the verifier in return that the verifier is supposed to generate randomly, and then computes a function of that challenge, the original private key, the original secret, and the original scalar that it created in the first round. Then it sends back the result of this function, and the verifier checks that the arithmetic for the scalars and the exponentiated elements holds. So in this case, the verifier generates the random challenge, sends it to the prover. To convert this to a non-interactive proof, which is needed for most of the blockchain use cases, because we can't have a verifier who is completely online all the time, we perform the Fiat-Shamir transformation. I'm not going to go into the whole random oracle model. In practice, what we usually do is we use a secure hash function with which, into which we put various parameters of the system, and usually in addition to the commitment to the random scalar k to which we commit in the first round, some additional message, for example, so that we can instantiate that this proof happens under certain conditions. For example, I'm proving something on this day in Rome on the 7th of May, and somebody else shouldn't be able to use it or under different circumstances. So the prover computes this hash and generates the challenge in this way from the hash. Then it finishes the protocol as if it was talking to the interactive verifier and sends all the necessary information to the verifier once. The verifier can then simply recompute the hash, recompute the challenge, and use it to check the correctness. So in practice, there are many things that can go wrong. So the first, most basic thing is you can forget the message. If you forget the message, then it means that you have created a proof which, when sent on the network or when published, can be easily reused by anybody else. So I proved my knowledge of the discrete logarithm once. Somebody else used the same proof because it's non-interactive, it's not bound to any conditions, and they can prove that they know the discrete logarithm without actually doing any work. An even worse case is if we forget to commit to the, if we forget to add the commitment to the nonce scalar into the hash. That means that the challenge is now completely deterministic, and the malicious prover can basically ignore it, use the information from this deterministic challenge, and create such parameters that would completely break the scheme without actually having any knowledge of the public key. So you basically, so the malicious prover can basically go and set such parameters that this signature, this non-interactive protocol holds without any knowledge. And there were a lot of examples of Fiat-Shamir attacks in the previous years. So, for example, for the last 4 years, every year, there have been published attacks. In 2023, there were several attacks on various proof systems, such as bulletproofs, Blanc, specifically on various implementations. Then in 2024, I think at the zkSummit, actually, there was a presentation on the last challenge attack, where Fiat-Shamir was implemented incorrectly within a particular Plonk instantiation, and the batching challenge was computed incorrectly. In 2025, there was a Plonky-free vulnerability, and the day before I submitted this presentation, I think AutoSec published several attacks on 6 ZKVMs with various vulnerabilities in Fiat-Shamir implementations. There are a few reasons why this keeps happening, especially in the modern systems. So the first is modularity. Right now, to develop something, you have to quickly be able to exchange components. For example, there is a new commitment system that is more efficient, like WIR comes out. You want to take out your pre-existing polynomial commitment system and put in a new one. Sometimes when you're doing that, you end up with mistakes. The second is rapid development, because we are, instead of trying to create one secure specification and then implement it correctly, I don't know, like for ECDSA, let's say we have proven systems that are evolving constantly. There's rapid development, there's no specification. It's very hard to basically write out the whole layout of the full protocol, which means that it is hard to catch these in a paper. And last thing is that there are no, well, there are very few potential detection mechanisms. So, for example, there are special frameworks such as Merlin and Decree, which help, but they basically rely on either the developer completely defining the protocol beforehand, which makes it harder which makes it much harder to use modularity. Or, they also rely on the developer not leaving out any data, because like every submitted value has to be submitted directly into the transcript with them, which means that if somebody just decided to compute something on top of the values that they didn't put in the transcript, or they just forgot to put something in the transcript, there's no way that this can be caught. Obviously, this kind of complexity also affects the AdStack network, because we have a very complex system with lots of recursion. So, for example, we have several layers of application circuits and kernel circuits being recursively folded with special speed-up mechanisms for recursive folding. So all of the elliptic curve operations, for example, go into special elliptic curve operation queue. Then at the end of all of these recursion, we have a special hiding kernel that now uses zero knowledge. Before that, zero knowledge is not being used. All the elliptic curve operations then go into a special VM that is done not on the main curve that we're using, BN254, but on a special cycle curve that proves the operations, and then we go into a special circuit that proves the correspondence between what is happening in ECCVM, all of those operations, and the original OpQ that is in BN254, which is the translator. And then from all of this, we get one single proof from multiple components. And even at a single recursion step, we also have several components. So we have the basic hyperplonk version with lookups, which is called OINC internally, that goes through the sum check, and then we use Hypernova to accumulate the claims and to accumulate the claims and eject them into the next step of recursion. So tons of components, and this basically creates a recipe for disaster for our system, because, well, one, we're using recursive verification on the client. There is no training wheel. There's no way for us to check that somebody hasn't injected something malicious there. There's huge modularity with different components, OINC, sum check, Hypernova. Then we have deferred elliptic curve operations that go into the ECCVM and the translator. There are many flavors. We have the ZK sum check. We have the non-ZK sum check. Then we have two different curves that we use, and there are special protocols like ECCVM, translator, and merge protocol to actually bind individual ECCU operations and pull them into this whole queue that is getting proved in the end. So we decided that we need to do something to catch these kind of issues within. And the first thing that we decided to do is to make a single recursive transcript. The basic idea is that we are not injecting values one by one into it. So instead of sending, for example, by one, a commitment to witness wire, you just take the whole proof as field elements and you send it to the recursive transcript. And then when you want to receive on the verify side an element, you actually call receive and it automatically adds that to the buffer for the hashing for the future for creating challenges and gives you the element that you want to use in an appropriate format. That means that every time that we ask for the challenges, all of the previous data is being used for the hashes. It means that there can't be a situation where we are rehashing and we forgot some previous element. Unfortunately, this obviously doesn't protect against all the attacks. This is a very simple architectural choice. And especially because we are using recursion, there can be such simple things as, okay, the developer forgot to use the transcript, let's say, and decided to recompute a particular batching challenge natively and then reinsert it as a witness into the circuit. So for example, we have two commitments that go into the transcript and then the challenge is recomputed separately just using their native versions instead of, and then re-injected instead of using the challenges from the transcript. And obviously we'd like to catch this kind of attack because it's one of the most basic ones. So the thing that we decided to do is to add additional information into each of the elements that we use when we're describing the algorithm of the recursive verifier. So let's say we have a special element field that represents field operations. We add in the tag there for all the operations on various, for the group operations, like for example, the cycle group that represents Grumpkin, or for non-native operations like big field. We have this field called tag, which represents some information about the element. Every time we do any arithmetic on these elements, we merge the tags, so the new tag is the result of the previous ones. Any arithmetic automatically does this. The developer doesn't have to think about it. So what we can do is then create a set of rules that will simply detect the most basic problem. So at stage one of the origin tag mechanism, we add the information whether this particular element is supposed to be a constant. So this is either an element that is not even injected as a witness into the circuit. It is automatically put into the selectors. Let's say whether it is a free witness, it didn't originate from a transcript at all, or whether this element was ejected, was taken from the transcript. It means that it is either a challenge or a value that was taken from the transcript and takes part in the hash and takes part in the whole recursive verification. And then we have several rules. Whenever a constant operates with a different element, it preserves the tag of that element. If we have two free witnesses operating, we get a free witness. And if a free witness operates on an element received from the transcript, then we immediately generate an exception because this shouldn't be happening. So this immediately protects us from this most basic problem. When two elements from the transcript interact, that is completely okay. So as a result, we have a mechanism which immediately solves the issue in the first attack. So we have a commitment that is derived from the transcript. We have a challenge that is completely independently created as a free witness. We try to combine the tag from the two, and as a result, we get an exception, which prevents us from making this mistake. So obviously, there are some other attacks. So for example, a lot of the problems in Fiat-Shamir happen if we have two separate sub-protocols, let's say. One of the issues that can arise is that the challenge that is used for batching some of the information is derived just from one of the sub-protocols. Like in this case, we are talking about Plonk. As a result of the recursive Plonk verification, you usually end up with two group elements, which should be used for pairing. You can go and batch 2 different recursive Plonk proofs. So you have 4 elements, you can batch them so that you end up with 2 pairs once again. One of the vulnerabilities that I have seen in the past is that the batching challenge is generated just from the last one of them. This means that the malicious prover can simply change the values that are derived from the first element, from the first proof in such a way that the whole proof holds and the result of batching is considered correct by the recursive verifier. To detect this issue, we add additional information into the origin tags, which basically tracks which transcript these values are descended from. So if you are instantiating a different recursive transcript that uses completely different data, then it will have the ID of that transcript, and whenever values from 2 different transcripts, from 2 different Fiat-Shamirs meet, we immediately throw, because why is this happening? Why are you using, for example, the challenge that belongs to one on the other? This is ripe for a vulnerability. And as a result, when we're trying to merge the tags from 2 different Plonk, recursive Plonk verifications, this is going to throw and this is going to protect us. The last thing that the origin tags can protect against is the attack that is also quite widespread. I think in the case of the last challenge attack and in the case of the Plonky-free vulnerability, one of the issues was that the batching challenge was derived not from the end, not at the end of the protocol, but right after the commitments to the wires. So after that, you get the evaluation of the wires, and you apply the batching challenge to the evaluations, even though the batching challenge was derived before those, which means that you can provide such evaluations that will always pass your further checks. So to protect against this, we've extended the protocol with round provenance. Basically, we have a special field, which is 256 bits, where the lowest 128 bits represent that this value is derived from some value in the round round with this number that was submitted by the prover. The higher 128 bits show that this value has in its history of derivation a challenge from the same round. Then we can add a mechanism that checks that whenever we apply a challenge, the maximum challenge round in this particular value is more equal than the maximum submitted round. That means that we are basically not applying a challenge to a value that is that was submitted in the later round. As a result, when we're trying to combine a challenge from the previous rounds, we immediately get a throw, and this protects us from these batched challenge attacks. There are a few problems even with these mechanisms. One is that all of the detections still have to be manually handled. There are some false positives, such as, for example, the last step of the KZG is when you create the quotient. So this is the last submitted value. There are no challenges after that, which means that when you're computing the recursive verification of KZG, this round provenance is going to fire off, and the developer has to go in and say, okay, this is a false positive, this is something we can ignore. Across our code base, across the Aztec packages code base, there are 10 high-level and 25 low-level false positives that we had to get rid of, but so there is some work, but it basically has to be done once, and then you are just continuing using it. It also doesn't protect against fundamental logic bugs, obviously, so if your protocol is incorrect, it can't really help you. And a reviewer can treat a positive as a false positive, unfortunately, so you can't really protect against that, only by maybe pushing it into an LLM. So, yeah. To summarize, Fiat-Shamir is hard to implement correctly. It is possible to create automated detection that is going to help you find these issues. It doesn't defend from all the bugs. It still needs some oversight, and developers can still make mistakes, but it does help. I'd also like to thank Luke, Sergey, and Lucas for their help with the mechanism. That's it.
Great. So thank you very much. Have we got any questions for the moment? No? Okay. Yep, one over here. I think I'm closest. Race.
Fiat-Shamir has been around for so long. Do you have any insights into what makes it so, what makes it so hard to implement correctly? And is there any hope of meaningfully moving past that?
Well, I think right now we are creating protocols which are huge and just created from many scraps, basically, right? We're pushing a lot of stuff together. We are not usually formalizing how it interacts. There's no single proof usually for the whole protocol. So as a result, it is hard to check. And then people simply make mistakes anyway. So some value can be just forgotten. You're not really checking that the code 100% fits the specification. So it's just a huge complex thing. So it's easy to make a mistake. So I don't know how you can fix it completely, unfortunately.
Make no mistakes. Cheers.
Thank you.
I didn't quite understand how is difference between this. How is this different from Maryland? Like, you're adding tag at every step, right?
Yes, all the interactions. So you are adding two values. It will immediately show you the issues. Yeah. And this doesn't have a formalization of the protocol. So for any transcript that you use, you take out the values, for example, out of there. You start using it with a different value that is not connected to this at all. It will trigger an exception.
So each operation you do add tag?
Yes. It's not just the original elements that just exit the transcript. All the verification, all the arithmetic every time computes the conjugation of those tags.
And then tag has all the input to that operation?
Yes, so it basically, every time it computes from the previous ones a new tag, and it says, oh, is there a violation on this one or not?
So you don't really, like this is automatic, like you write and then somebody, like there's a compiler that take the current code and add the tags step to it, right?
It's just part of the type system. Our recursive verification is written out as in-circuit types in C++. And so you just do A plus B, and automatically under the hood those types.
Yeah, the compiler adds it. Yeah, I understand. Thank you very much.
Okay, any more questions? No? Okay, thank you very much, Innocenty. Okay, so a few things to let you know. Next up, we've got the quantum question panel happening in here, but that will be in about 15 minutes. But I'd say don't go anywhere, because once we've had that panel, there's also going to be some money behind the bar for your drinks. So I'm sure you might want to hang around for a few of those. So yeah, you could probably take like a 10-minute break, even if you want to just stay in here and hang about, but we'll get ourselves set up and then we'll have the panel. Okay, we'll see you in a minute.
Heat treatment.
Hello, everyone. Hi, how are you feeling at the end, almost the end of this zkSummit14? How are you feeling? Feeling good? Was it good? Did you learn anything today? So we are here for the final session on this stage. It's a panel with the topic being the quantum question. Quite vague, quite open, maybe a little bit on purpose. The format of this is going to be interesting. We are awaiting one of the panelists. So we are going to kick off with a little bit of an introduction to the problem space. I feel like most of the people here probably do know why quantum computers could disrupt the cryptography we know and love. But there are people watching at home that might not be as familiar. And so I kind of want to go back to the reason why we're even having this conversation. What's the problem with a quantum computer for ZK? What's the problem with a quantum computer for blockchains, for general cryptography? Oh, but first I should introduce who's here. So it's myself and Nico.
Hello, hello.
And our panelist, one of our panelists for now, Justin Drake.
Yeah, this is the highest moderator to panelist ratio. You'll find.
Okay, so yes, that is the question. Why are we even afraid of quantum? What does it mean? What will it do?
Absolutely. Thank you so much for having me on this IRL podcast. So the main issue with quantum is that they can take public keys and turn them into private keys. So normally only the asset holder should be able to have the private key, but now anyone who has a sufficiently large quantum computer can have access to these private keys. But not only do the signatures break, but a bunch of other things break. So, for example, the snarks that we know and love that are pairing-based, things like Graph16 and Planck, those break. And even relatively sophisticated infrastructure like the Ethereum data availability will break. So that's based on KZG. So for Ethereum, we actually have, in some sense, one of the worst scenarios where we have 3 layers, each of which need to be updated. At the consensus layer, we have BLS signatures. At the data layer, we have KZG. And at the execution layer, we have ECDSA signatures. And all of these have to be upgraded.
All of them would break.
All of them will eventually break, yes.
And that's just the way you're describing a quantum computer, you're talking about it as though it exists today.
Yes.
But it doesn't. Like, these aren't broken today.
Right.
Okay.
So they will be broken once we have a so-called CROC, which is a cryptographically relevant quantum computer.
I see.
And in order to achieve cryptographic relevance, you need to achieve a certain amount of fault tolerance. So you need to be working with bits, basically. Right now we have analog quantum computers. And the error correction to get from analog to binary is actually non-trivial. And then once we do have fault tolerance, which we're basically almost there or even there, we need to scale to sufficiently large number of so-called logical qubits. And for cryptography, we're talking roughly 1,000 logical qubits.
And where are we at? Like, because there are quantum computers today that are able to do something.
Yes.
Yes?
So
I've actually never been completely clear on that.
Yeah, so when you want to look at real quantum computers, you shouldn't be thinking in logical qubits. It's just a layer of abstraction which is too detached from reality. You want to be looking at the nitty-gritty, so-called physical qubits that are the equivalent of transistors for quantum computers. And it turns out there's different compilers to go from logical to physical. And one of the big breakthroughs just in the last couple of years has been unlocking this compilation, which is 100 times more efficient than what we had in the last few decades.
Okay.
Please.
Yeah, sure.
So I am not an expert on the physics of this at all. but I've talked to people who are, and they say that number of qubits is not really the problem, because you can replicate a circuit. The size of the circuit is not the issue. The issue is that there are still engineering problems with the error correction. But when you solve those engineering problems, the number of qubits is going to explode, because the reason they're not making circuits, large circuits at the moment, is not that they can't, it's that there's no point.
Oh.
So maybe can we introduce a lot of the concepts here? So we have our logical qubits, which is, we know Shor's algorithm breaks discrete log. So that's written, we need a certain number of logical qubits, is that it? Then physical is what we can build. We have a translation from one to the other. What's error correction and why do we need it here?
I mean, the problem as I understand it is still getting, you solve one set of engineering problems, and then you find another noise floor.
Of course.
And the noise floor is still too high to make a computer that actually works. But I mean, the bet of the people who are working on this is that there will be a point at which you solve the last engineering problem that is needed to make them work. So, I mean, that is why I think that I believe the estimates that we need to be worried about upgrading all of our protocols within the next, well, protocol evolution takes a long time, so 2 years, in order to prepare for
an actual break.
A break in the next 4 years.
We should hold on timeline, because I feel like there's going to be lots of opinions here.
That's a big question.
But just going back to what you were describing, this history to the present, you had listed like an amount of, I forget what the value was, but it was like, this is what we need to break cryptography. What was that again?
1,000 logical qubits?
Yeah. So what do we have today?
So right now, we don't really have logical qubits.
At all?
Right.
Okay. This is important, I feel.
So we have proof of concept demonstrations that we can do logical qubits and we can do error correction. But there's two things that really we need. One is the quality of the physical qubits to be good enough. And this is measured in so-called fidelities. And what we need for practical error correction is 3 nines. So for every 1,000 operation, you need your gate to work 999 times. For most platforms now, so if you take trapped ions or neutral atoms or superconducting, we're now at this point of 3 nines of fidelity. So that, in some sense, is solved. The other kind of big issue is so-called real-time decoding, where in order to do the error correction, many times per second, maybe 1,000 times per second, you're going to be measuring these dummy qubits that will tell you whether or not there are errors. And then based on what you measure, you need to be applying real-time corrections. And this is a purely classical problem that needs to be done in ultra-low latency. And the engineering just hasn't been done yet. You need to use basically FPGAs and GPUs, and you need to develop these low-latency decoders. And for some reason, like the physics is ahead of the quantum physics is ahead of the classical algorithms at this point in time.
The classical algorithm side doesn't need a quantum computer to be developed.
Correct.
Like this can run on the hardware that we have today.
Yes.
Okay.
And in a sense, there's a little bit of an analogy here with ZK, where real-time proving was this very difficult thing to do, and we got it. And now, there just needs to be some teams that do the same thing for real-time decoding in quantum.
Is that what those labs are working on? Like, does Google have a team doing that?
Yes, so a lot of the teams are working on quantum error correction and decoders, but a lot of the different teams are working on the different physics for the so-called different modalities. And I happen to have a favorite modality, which is the so-called neutral atoms. And there's kind of two reasons why I really like neutral atoms. The first one is that they have this superpower called reconfigurability. So you can take 2 qubits and move them physically to be close to each other, and then you can untangle these 2. So if you have, for example, 10,000 qubits, you can pick qubits that are far away and just have all-to-all connectivity. And that means that your compilation from logical to physical is about 100 times more efficient. So if you have superconducting qubits where they only have nearest neighbor connections, so in a grid, they're only connected to the 4 nearest neighbors, your ratio of physical to logical is going to be 1,000 to 1. So that, that's what Dara was saying, that if you take Shor, which has 1,000 logical qubits, and then you have another 1,000 to 1, you're going to end up with 1,000,000 qubits, which there's no way you're going to fit on a single quantum processor. A single quantum processor can only fit roughly 10,000 qubits. So if you want to run Shor, for example, on superconducting platforms, you're going to have to do networking, quantum networking. And this is a thing that we haven't really solved. So in the context of neutral atoms, you don't need networking, because you only need 1,000 times 10, which is 10,000, and we can fit 10,000 qubits on a single neutral atom processor. And then the other reason why I'm bullish about neutral atoms is that it's much easier to get to the number 10,000. So if you look, for example, at superconducting qubits, today they can only fit a few hundred. And part of the reason is because they have all of these yield, they have to fabricate the qubits, and they have all these yield issues, and as soon as you scale, the yield basically goes to 0. And it's just very difficult. And then there's this other platform called trapped ions, where basically you have these charged particles, and they don't like being close to each other. They repel each other. So it's very difficult to get 10,000 in a single box.
So for the neutral atom platform, so you were talking about physically moving the atoms from one place to the other. This is not something that we do in conventional integrated circuits. So how difficult is that in practice? And in particular, how difficult is it maintaining coherence?
Yeah, so in 2021, I believe it was the Harvard group that showed a Mario animation where there was 16 by 16 grid, so 256 qubits, and it was just showing Mario moving as a video. And so you can control the qubits extremely well, and it takes just a few milliseconds to move them from one place to another. And the decoherence that comes from the movement is actually well below the threshold that you need to do error correction. So that's not the bottleneck.
Okay, yeah.
Cool.
So that a few milliseconds, that would be the cycle time. But I guess for an algorithm like Shor, where you have an exponential speed up, technically you have an exponential speed up for Grover as well, but where kind of it's just polynomial in the security parameter, you don't need that many cycles, right?
Yeah, so you need about 100 million cycles. So the expensive cycles are called the expensive gates are called Toffoli gates. You have roughly 100 million of them. Each one will consume roughly 1 millisecond or so. And then you end up with roughly 10 days of computation to run Shor.
Okay.
I was just trying to work that out in my head. Yeah, that's about right.
Okay, so we're going to do a little shift on this panel because we just had one of our guests arrive. Hi. Dara, if you want to, do you want to stay?
Yeah.
Okay. Perfect. Yes. All right. I want to welcome Dan Bonnet to the stage, the guest of my 400th episode as well. What an entrance. Hi. You just got off a plane.
I literally just landed 2 hours ago.
Thank you so much for coming.
Rushed over here as quickly as I could.
Thank you so much for coming. So just to bring you up to date on what we've talked about so far, we were really looking at what are quantum computers? What can they actually potentially do with cryptography? But what do you need in a quantum computer to actually achieve that? And then we were trying to figure out what exists today on the theory, but also what exists in practice. Justin just introduced neutral atoms. We kind of started to give a little bit of the we started to distinguish between the different types of quantum computers. I did want to say something that I think we said on our show, which is like when you see quantum computers in the news, when you see this thing with all these wires, that is the superconducting version of quantum computers. And what you were talking about with neutral atoms is something else. What do those look like?
So neutral atom quantum computers are in an enclosure of roughly 1 cubic meter. There's no fancy cooling, it's just lots of lasers and lenses. And in the middle, there is this very small vacuum chamber, which is maybe 1 cubic centimeter. And then within the vacuum chamber, you have these atoms floating, which are like roughly 1 cubic millimeter. And one of the cool things is that it's mostly off-the-shelf optical equipment, and the total cost of the machine will be a couple $1 million. When you compare this to the superconducting platform, each of these wires that you talked about, there's at least 1 per qubit, actually multiple, and each wire costs about $1,000. So if you need 1 million qubits to run Shor, that's billions of dollars just in the wiring right now.
Whoa. All right.
The difference is that it's much faster. So the superconducting
Yes.
qubits are
Exactly.
faster computers than the neutral atoms.
About
But they have other problems like connectivity and so on. I don't know if you already talked about that.
Well, I think, Justin, you listed the things you liked about neutral atoms, but I don't know if we shared these sort of disadvantages.
Yeah, so neutral atoms are like great at everything except one thing, which is the cycle time. They're about 1,000 times slower. So for Q-day, what will mark Q-day, I think more likely than not, it will be something like neutral atoms and unlikely to be superconductors. But in the long term, we want our computers to run extremely fast, and so that's very bullish, the faster platforms. There is another disadvantage of neutral atoms, which is the so-called fidelities. So there's some platforms like trapped ions that achieve 4 nines. And if you go below 3 nines, significantly below 3 nines, then you gain a lot. But neutral atoms have 3 nines, and that's good enough for error correction.
Cool.
You said floating. This seems like another fundamental difference from conventional circuits.
Yes. So you have these optical tweezers, which are basically beams of light where the atoms like to stay where the light focuses. And there's different types of tweezers, but one of them is called a bottle, where basically you surround the atom with light, and the atom is kind of repelled on all sides by the bottle.
Wow.
Yeah.
All right, so now that we've done this primer on quantum, types of quantum, let's bring it back to cryptography and breaking it, or not. Like, there have been, the idea of a post-quantum cryptography was presented many, many years ago. I think, actually, who first was working on that? Was it like the Stark team?
There are many paths to post-quantum cryptography. I mean, there's like 5 or 6 different paths, and so you can't really say when exactly.
Okay.
I think as soon as Shor's algorithm was introduced, people started thinking about what do we do.
And they started to make this.
Yeah.
Microphone closer.
Oh, sure. Microphone close. Okay.
But okay, so yeah, like what do we like? There's a question, which is the hot button question, I think here. Actually, there's 2 questions. One is, do we think there will really be quantum computers? Do we need to be worried? And the other is when, if so. And so on this panel, I think we were talking to a few of you, I don't know, in the audience. We were trying to find someone who really didn't believe that quantum computers would ever exist. And we actually didn't find that person. You might be here, but we didn't get a chance to talk to you. We will open up the floor after, so if you do feel that way, we want to hear it. But we were looking for someone to join us on this panel who was very bearish, who felt that quantum computers will remain in theory for a long time, that we can rely on the cryptography we have today. On this panel today, I just want to check, do any of you believe that? Do you think that quantum computers will never happen?
So my position is that we have to assume that they will. Actually, that's been my position for a long time, but we have to upgrade the protocols anyway. I also believe that they will happen, but that almost isn't relevant for cryptographic engineering. We need to update the protocols.
Okay.
And it turns out that we get simpler protocols because they just use symmetric cryptography more often. And so we should use this as an opportunity to simplify. If I take Zcash as an example, so Sprout is a lot, actually, ironically closer to being post-quantum. It's just the proof system that is vulnerable, not the thing that you're proving. The cryptography of the payment protocol is just based on hash pre-images. So, and then when we went to Sapling, in order to optimize it, there was an observation, which I think comes from the COCO paper, that actually doing elliptic curve cryptography over the right fields and curves is very efficient in circuits. So we took advantage of that, and we needed to because the Sprout circuit was really inefficient. But at that point, we didn't have algebraic hashes that we were confident in. So that was the reason why we went to elliptic curve cryptography within the circuit. Now that we have things like Poseidon, so despite the recent cryptanalysis of Poseidon 2, Poseidon 1.1 is fine. Just use it, it's fine.
So now that there are hash functions, you would probably just
and
go
so
with
now
it.
we know how to do a lot of fancy cryptography just using symmetric primitives. And we don't need them for payment protocols. We don't need them for a lot of other things. So we should go back to using that in the post-quantum world. We still do need kind of semi-structured things like lattice-based cryptography, but it's.
Yeah.
I don't think we'll miss elliptic curves and RSA and discrete log over finite fields.
This is quite.
Just throw
this is
away,
surprising to have Dara here saying this, because a few years ago you didn't feel that way. And of the people here, like, were you the most bearish up until recently?
I was quite bearish, but also I contributed to Sphinx, which became Sphinx Plus, which became SLH DSA, which is now standardized. So I obviously was thinking that this is something that we needed to worry about, but I was quite skeptical that we would even be able to get to the first step of Shor's algorithm, which is create a uniform distribution over qubits.
This makes me want to ask now, like, is there anyone in this audience who does not believe that a quantum computer, or who does not think a quantum computer will ever truly exist, that it will remain in the realm of theory? And it's okay to put your hand up.
Actually, I do feel like I need to address that, to be honest, because these are just opinions. At the end of the day, we don't really know, right? I mean, quantum computers are n years away from for an unknown value of n. Whatever opinion you hold, you could be wrong. And do we really want to bet the world financial system on an opinion that could be wrong? And so I totally agree that it doesn't really matter at this point whether these computers will exist or not. The fact that it's a threat and the fact that it erodes trust in the blockchains means we have to adapt. I can tell you that one of the things that's most depressing to me is if we make the shift and we move away from our beloved elliptic curves and move to far less efficient systems, and then 100 years go by and still quantum computers don't exist, I think that will be a crazy, depressing world to be in. So if we make the shift, we do all this effort to transition all the blockchains to systems that are harder to use, for me, harder to teach. It better.
That's the real issue.
That's the real issue. It better be that quantum computers are real and they're coming. Otherwise, what the heck?
Okay, I'm more optimistic about this world where we never get quantum computers, but we have all of the complexity in our protocols. Because as I pointed out, we add complexity in some places and we remove it in others. So it's all actually a bit of a wash.
Jens, you just put your hand up. I'm wondering, maybe would we be able to switch places?
Oh,
Do you want to join?
Musical chairs.
Or do you want to just ask a question?
I will gladly yield to Jens.
This is an unusual panel to start. So why don't we keep going?
I hope somebody else will also have a comment.
So this, by the way, is a bit of a throwback to a type of panel I used to do, which was called the park bench panel. We didn't necessarily start this panel with that idea, but this will be a hybrid. We might talk more about that. Anyway,
Yeah.
what are your thoughts here?
I think my question is sort of like, okay, suppose quantum computers come about. What is actually going to be the impact, right?
Suppose quantum computers?
Yeah, quantum computers.
Quantum computers, yeah.
Yes.
Post quantum computers is the next step.
It's just so ingrained in, my
the
wiring. But I'm wondering sort of like what we should think about the consequences, right? Because as I see the space, we have like Shor's algorithm, Shor that can do things. We have Grover's algorithm, and then we don't have that much more, is my understanding, right? So
actually, that's not quite true. We have a lot. In fact, there's a whole website. It's called the Quantum Algorithm Zoo. It's actually worth checking out.
Oh.
There's a huge number of algorithms that we have. It's true that a lot of the problems are sort of algebraic in nature. So this stuff is very good. Well, these things are very good at solving problems that have periodicity built into them. Yeah.
Okay.
So they're kind of algebraic in nature, but there's a huge number of problems that we can solve with these.
And would you say that they're sort of like different in nature from what Shor's algorithm can do? Or is it like derivative of that?
Yeah. They go quite beyond Shor's. Shor's algorithm is pretty simple. It's been 30 years, but now these algorithms have actually gotten much more complex. And I mean, they're still solving sort of computational number theory, computational algebra style problems. But yeah, it's worth checking out. Check it out. The Quantum Computing Zoo, Quantum Algorithm Zoo. It's a really cool website.
But I guess Shor's and Grover's, are those the only two that are relevant for blockchains?
Grover is not relevant.
Okay.
It's really only Shor. Grover is not relevant.
Yeah.
I hope everybody understands this, right? I mean, so Grover gives you a quadratic speedup with a huge constant. The constant dominates the quadratic speedup for all real world problems. The problem has to be unrealistic for Grover to become asymptotically practical.
So is Shor the only one
that affects cryptography?
That affects not cryptography, but blockchains. This, like blockchains popular ones.
That's a tricky question. I mean, so it could be that tomorrow somebody discovers a lattice algorithm, a quantum lattice reduction algorithm, and then all the blockchains that rely on MLDSA and Falcon would be in trouble.
Oh.
So we don't know. I mean,
Yikes.
right? I would say the field of quantum computing right now is really at its infancy because we don't have a computer. So that the number of people, it's like, the number of people who were writing code before computers existed, you could count on one hand.
Yeah. Because that's what that is. It's an algorithm that would only work once a quantum computer exists.
Exactly.
And you were saying there's this page full of all sorts of algorithms like that, but
we haven't really, we've only begun, once the computers exist, now there will be, everybody and their uncle are going to start designing algorithms for these things, and then that's going to unleash a lot of ingenuity, creativity, and I think that's kind of where the applications will come in.
I did not realize that was the framing. This is very helpful.
Yeah. So I can think of one other thing that's quite different in the quantum world. There was this beautiful work on commitment schemes, right, where the classical definition of a commitment scheme is that you can not create a commitment and two different openings to that, right? And where it's actually a little different in a subtle way in the quantum world, because you can imagine creating a commitment somehow in an entangled form of two openings, and then you measure one of the openings and you reveal that later on. But then, so like by the non-teleportation theorem of quantum theory, that means that the other opening is not accessible anymore. So you can sort of like, which is really weird to think about, right? It's a very subtle way that the classical way of thinking about commitment schemes fails.
It doesn't work there. It doesn't transfer.
There's a lot to say about that. But,
do you want to?
No, but we can move on.
Okay. So I will put the question again out there. Are there people who don't think that there's going to be quantum computers? You? You have a remark?
speaker?
I don't know.
Swap?
No, I guess, yeah, this is the hot seat.
I wasn't planning on this, but...
Like, this is what this panel is now. It's nice.
So it's not really my opinion. It's actually the opinion of Serge Haroche. He's a French physicist who won the Nobel Prize in 2012. And in '94, he wrote a paper called, I think it's Quantum Computing, Dream or Nightmare, in which he basically explained, oh, by the way, he got the Nobel Prize for developing methods for measuring and manipulating individual quantum systems, so he knows what he's talking about. And in '94, he wrote this paper saying basically that we would never have a useful quantum computer. I don't know if his opinion has changed, so my question was whether you know if his opinion has changed since '94.
So in 1994, which is the year that Shor was discovered, there was a whole debate. And the debate basically was around the quality of the qubits. In order to run Shor, you need really, really high qubits, high quality qubits, with fidelities on the order of like 10 to the minus 10 or 10 to the minus 12 or something. And no one believes that you can do that with naturally occurring qubits. And then what happened 2 years later in 1996 is that people discovered error correction. And actually it was Shor who came up, I believe, with one of the first schemes. And then in some sense that's partially settled the debate where you can take these imperfect qubits and you can compile them in a way into bigger clusters such that the cluster is one virtual logical qubit. And so I think this opinion from 1994 was pre-error correction, and it probably has been revised since.
Okay.
But I will go along. Let's continue with the thought. So there is a group of people who object to quantum computers ever existing, and the argument is, well, our understanding of quantum mechanics is wrong. Yeah, and so nobody has ever done experiments with superpositions of so many particles. And it could be when we start to scale up the experiments, all of a sudden we discover new physics, and Schrödinger's equation breaks down. Quantum mechanics is incorrect. Yeah,
well, rather
that could
incomplete,
happen.
Maybe.
What?
Rather than incorrect, maybe incomplete.
Yeah, that could happen. And I can tell you, if that happens, for example, there's a paper that just appeared last year that says the universe only has finite precision, so therefore quantum mechanics is only correct up to certain precision and not beyond that. If that turns out to be true, then Shor's algorithm will never be implemented. The cool thing is we learn new physics, yeah? And this is like a once-in-a-century discovery of new physics. So this is like a win-win.
But we just migrated all of these systems, Dan.
We just yeah. Well, then we can migrate them back, and BLS gets to live again.
You have physics to teach.
Because you want BLS to survive.
There you go. Yes, exactly. So actually, it is. I have been thinking about this quite a bit. Actually, like what happens if we do the migration, we wait 100 years, and a quantum computer doesn't appear? Do we migrate back? I mean, how long do we have to wait before we migrate back?
Also, won't all of those, like the types of cryptographies, the efficiencies, like there is progress on all fronts. Like it's possible that they start to match the elliptic curve cryptography. Come back.
By the way, that's not to say. So I should say, by the way, my thinking has changed quite a lot, and that I used to be quite a skeptic about the construction of these of the computers, just because of the very slow progress that we saw. Like with NMR methods don't scale, other methods are noisy. I have to say, with superconducting was a big step, and then these neutral atoms, that has kind of changed my mind. Both Justin and I have been talking to a lot of the physicists who are building these systems. I can tell you, the conversations, they freak me out. Like this stuff is real. You read the papers. They're running computers for many hours, maintaining coherence for many hours across a large number of atoms. These machines are not difficult to build. One group says it's off-the-shelf equipment. Another group it says custom equipment, but relatively simple. You see, there's like over 10 startups now going after neutral atom architectures because they're so easy to build. It makes sense that startups would go down that path. You see NVIDIA actually. By the way, I don't know if you brought this up, but quantum error correction, interestingly, is a hard classical computing problem. Yeah, I don't know if people understand this. One of the bottlenecks in building a Shor quantum computer is actually the classical computation that has to be performed to do the quantum error correction. That is, right now, the gates operate at millisecond rates. The quantum error correction that Atomic is reporting operates at seconds per gate. This is a classical computation. The classical computation is slowing down the quantum computer. So NVIDIA actually got into this game, and they said, we know something about speeding up classical computations. So actually, they're hoping that this is a new market for the GPUs, basically running error correction for a quantum computer, which I think is pretty interesting.
This is a constant factor engineering problem. It's fine. And this is going to be solved.
I agree. If the only problem is classical computation, we'll solve that. Yeah. That I'm not worried. Just right now, there is a compute problem. And so it's interesting to see how things are progressing there. So I'm actually, maybe I was playing devil's advocate. And yes, maybe we will learn new physics and Shor's algorithm will never be implemented. But when you talk to these guys, when you see the scale of the experiments they're doing, what was it? The last one is 10,000 qubits. Oh. Oops. Forget I said that.
Yeah, forget you heard that.
10,000 logical
physical,
qubits.
Physical. Yeah.
The other experience I've had that kind of has moved me towards the quantum computers is likely possible is the experience of being wrong on AI. So I made a prediction in 2000 that we would not have computers passing Turing tests until 2050 at the earliest. And clearly I was wrong. And so that experience of being wrong on a long-term prediction about technology has made me more cautious about things like quantum computing. And a lot of experts seem to think that this is going to work. So I don't know the physics well enough to contradict that. And the fact that that fits in with, we have to upgrade the protocols anyway, yeah, I think it's fairly clear what we should do.
Actually, I want to make one more point, though. So, okay, so we talked about this in the show, but I want to bring it up to this audience and see the reaction. I do worry that there's a bit of a rush to post-quantum, and that rush to post-quantum is really quite dangerous. And there's an example I want to give, actually two points I want to make. The example I like to give, I don't know how many of you have heard me say this already, but let's just say it's a hypothetical example, even though it's not. This company came and told me that they want to move to post-quantum. Today, their classical keys live inside of an HSM, but the HSM does not support MLDSA. So what do? They take their keys out of the HSM and do the MLDSA in a CPU in the clear. The minute you do this, you are way more likely to be attacked by a regular hacker than by a quantum computer. Yeah, that's the result of a rush to post-quantum. So I want to caution people about the rush to post-quantum. The correct action, in my mind, there is don't take your keys out of the HSM. Go lean on your HSM provider to provide MLDSA support as quickly as possible. Yeah, this is why Google sets this 2029 deadlines, so they can lean on the hardware providers to say, because of you, we are not meeting our deadline. Yeah, so you better get your act together. That's the first point I want to make. The second point I want to make about the rush to post-quantum is even if you set 2029, this is a bit for you, Justin. Even if you set 2029 as your target deadline, this is a bit delusional because just last month, actually, Intel came out and said that their processor is going to be post-quantum only in 2030. So you might have migrated your system to be post-quantum, but the processor you're running on will accept microcode changes signed by a pre-quantum signature until 2030. So yeah, just be careful. This is a very complicated process. And we should not rush it.
It is reasonable for your attack model not to include adversaries who have physical access to your processor to upload microcode updates. Well, actually, I guess it doesn't require physical access.
Sure, we can start defining post-quantum however we want. Yeah.
Just a note, there was... Oh, there. Perfect. Okay. We have someone coming up who had a question, and then Nico, you had a question next.
Yeah, I wanted to maybe reframe your question in a way that might get more people in the audience to raise their hand, which is on the complexity theory side of things, which is we don't really actually know if, from a complexity theory point of view, quantum computers are actually better. I mean, we don't really know like is P equal NP or not. right? So from that kind of lens, there's a chance that there is a polynomial time algorithm to solve some of these cryptography questions, and we just haven't found it yet. Of course, we don't actually know the constants, but this kind of like is like a ties into maybe like some greater problems in computer science.
I have an answer. I have opinions. So what we're really doing when we move to post-quantum algorithms is we're getting rid of all of the dependencies on discrete log. That's, for most systems, that's what we're doing. That works just as well against a classical discrete log algorithm as it does against a quantum computer. And I always frame it as kind of we're fixing this protocol against a discrete log-breaking adversary. We're not specifically protecting it against a quantum computer because, as you said, Grover's algorithm is basically irrelevant. You should choose your key sizes long enough, but you should do that because of multi-target attacks, not because of Grover's algorithm.
Okay, fine. So there's one more switch, I think, and then we're going to wrap up our panel. But there is sort of the timeline question that hasn't really been answered. Your favorite.
Oh. But just very briefly, since you mentioned the risk of the rush to post-quantum,
yes.
Is there also any worry about rushing to lattices when we don't know enough about lattice assumptions?
Whoa.
Hash functions, I think we've seen for a long time, but yeah.
Justin, do you want to take that?
Hot potato.
I mean, there is also a question in the hash-based world, like, should we be rushing to Poseidon? And hopefully we won't be. And we're looking at all the alternatives, and we're trying to do as much due diligence as possible. On the lattices, I think there's like a real question as to whether. So we do know that I guess the assumptions are about 30 years old, right? So a lot of mathematicians have looked at them, but because there hasn't been an incentive to break them, to break real-world systems, maybe it's just not battle tested. On the other hand, the Merkle signatures that we're looking to deploy, the so-called XMSS, where the M stands for Merkle, these are 50 years old. And they're extremely simple. And I guess one of the comments that Dan made is that the cryptography that we're deploying is more complicated. Well, I'm hoping that it's in some sense less complicated, at least in certain parts. But yeah, like one issue with the lattices is that you have to be an expert in order to set the parameters. And there's also, as Dan mentioned, there's a possibility that we will find a quantum algorithm to break lattices. There's also a possibility, exactly, or a classical one. So if you want to build a system that is likely to last decades and centuries, I think that's just a personal opinion, hash functions are the way to go. Yes.
Yeah, I mean, you can do hash-based signatures. What was I going to say? So
I have something to
forgot
say.
my point.
Can I? So has anyone worried? So you talked about these quantum algorithms. Is there more focus? Okay, let me try to frame this. If there is the assumption that quantum is coming, will people focus more on these quantum algorithms instead of the classical ones that could break existing systems? Like, will we almost get like a mind share problem if everyone starts, like, if everyone buys into quantum?
Quantum algorithms, they're a superset of classical algorithms.
Okay.
So if you're designing a quantum algorithm, by definition, you also, or rather, if you're designing a classical algorithm, that's also a quantum algorithm.
But I'm almost wondering if the mind share goes too far into quantum and isn't then reusable in this classical sense. This is more like a social question, like.
I mean, the attention.
Sorry, random.
Sorry.
Random thought.
The attention. Sorry to interrupt. The attention on kind of post-quantum cryptography. That's how a lot of the isogeny-based systems like Zyte got broken. So, and they were broken not by a new algorithm, but because people hadn't noticed that there was an existing algorithm that broke them. That's a bit of an oversimplification, and it doesn't apply to all of the isogeny-based schemes, but that's a brief summary. So yes, there will be more attention on the algorithms that are being used in, the assumptions that are being used in post-quantum cryptography. That's fine because lattices, there's actually a lot of dependency on lattices even in conventional cryptography because it kind of LLL, so the main algorithm used to break lattice problems, is also used in sort of classical cryptanalysis against various things. So yeah, advances in those algorithms aren't just going to break the post-quantum stuff necessarily. Other thing is hybrid. So basically, if you're doing
did you say hybrid?
Yeah. Okay. If you want to upgrade your protocol to post-quantum encryption, say, then you should just use X-Wing, which is a hybrid of MLChem and ECIAS, basically.
Which is what is deployed on the web. But by the way, when Intel said they're going to become post-quantum, they mean they're going to implement MLDSA in their processor. And so, you know, if your processor for security depends on the security of MLDSA, you're kind of lattice-based regardless, whether you want to or not. So we're going to have lattices in our lives at any rate.
Would it make sense to talk about timeline? The reason I want to talk about timeline is because you're here, Justin. Because I feel like you're one of the most bullish people I know. I kind of quoted you, Dan, today to Justin. I said, you know, Dan says the 2029 date is more coming from the security teams, not from the physicists. And you disagreed.
Yeah, well, as Dan mentioned, we've been talking to the physicists recently, and there's been a lot of developments in the last few months. But yeah, if you rewind the clock to October 2025, I was actually on the bearish side of things. But what happened in October 2025 is that we organized this post-quantum workshop in Cambridge, and we had this guest invited speaker who happens to be a quantum entrepreneur. And he basically totally shifted the Overton window. He said, Shor's going to be coming between 2030 and 2032. And everyone in the room was like, ah. And he's had this prediction for 15 years now. And it basically hasn't changed. He just says, you know, you have this exponential growth, you just, you know, draw the lines, and it kind of lands there. And
you know, by the way, Kalshi disagrees with that. So the prediction market will give you odds against before 2035.
Okay.
Yeah, interested to see
Dan Bernstein's prediction, which he's also had for 15 years, is consistent with that one.
Okay, so where was I? Yes, so back then in 2025, my odds of there being a quantum computer by 2032 was about 1%. I kind of gave him the benefit of the doubt. It was a possibility, and you know, in our context, 1% is quite a bit, right? Because we're securing, you know, $500 billion. But then in February 2026, I got, you know, early access to the draft from the Google paper. And here, my odds went up dramatically to about 10% by 2032. And then when the paper was published, it was this concurrent publication of the Auto-atomic paper with neutral atoms. And I basically spent the last month and a half learning about neutral atoms. I've been obsessed. I've watched all the YouTube videos that you could find. I've read, you know, a bunch of papers. I've had conversations with like half a dozen experts. And now I believe that by 2032, there's a 50% chance that we'll have a quantum computer.
2032.
Yes, but the thing is that 50% chance is just way too high. Like, we have to upgrade before then. And I have this notion of the effective Q day, which is, you know, the working date that we have to have in mind by which, you know, there's sufficient chance that a quantum computer could arrive, and, you know, roughly speaking is, let's say, 10%. And I believe now that there's a 10% chance that in 2030 we'll have a quantum computer, and therefore we have to upgrade before then, hence the 2029 timeline.
So that's a security analysis that drives the 2029 number, which I think is exactly also what the Google security team did.
Yes.
2029.
Yes.
I interpret the 2029 number to say, let's talk about Google, not so much. The Ethereum Foundation is actually on a good path. But for Google, for them to transition their entire infrastructure to be post-quantum is a crazy hard task. They have to replace a huge number of their hardware devices, and it's a crazy hard task. It's most likely they will miss their 2029 target. But even if they miss it by 3 years, we're 2032, maybe we're still safe. If they stuck to their 2035 number and they missed that by 3 years, now we're getting into pretty dangerous territory. Yeah, and so I think this is part of the reason why they decided to set 2029 as a goal, and I think for the Ethereum Foundation, it's a great number too.
There's also the time taken to deploy infrastructure, which, as I said before, people always underestimate. So it's not just blockchains that have a potential governance problem that makes upgrades take years. It's PKI, it's HSMs, as we've already mentioned. So yeah, estimate 3 years just for people to get their act together.
The thing that I'm a little worried about is the public hears 2029, and they say, oh, wow, we're going to have quantum computers in 2029. No, that's not, I don't think that's the message. The message is the upgrade, the transition has to be done, or at least we should shoot for 2029, so that if we miss, we still have a margin of safety. It doesn't mean that 2029 is the date when we're going to have a quantum computer. Yeah, and even the, well, okay, fine. Maybe some physicists are aggressive about 2029, but even many of the people we talk to are, they give low odds for 2029.
Will we see signs along the way, or is it going to be a one-shot?
Okay, and that is a...
there's also the famous question of why have we not factored 21? I think those kind of all
those are two different
mixed in
questions.
together. Oh. Okay, yes.
Just
treat them separately then.
Maybe we should, well, I don't know, should we talk about 21 or should we talk about that we're going to see signs?
Go ahead, 21.
So 21 is not an easy problem. So when you write Shor's algorithm for factoring 21, that's about 200 gates, yeah? Today, we can't do 200. Actually, I guess they said that maybe without replenishing, they can get roughly to 200.
Well, you need error-corrected gates, which we don't really have in real time now. Right?
Well, that's my point. I mean, okay, so they talk about replenishing, but definitely 200 gates, we have to do error correction. So the first thing is you have to get error correction to work. Error correction only started working in 2024. So this question of 21 was like irrelevant before 2024. Yeah, now that things are starting to work, 21 is coming within scope. In fact, it's interesting that they were saying they might be able to do it without replenishing, which is still with error correction, but without replenishing, which is interesting. It's just that they're not interested in doing that. Why would they factor 21? That's like the question they always ask. So right now it's kind of it's maybe on the boundary, but within a year or two, the circuits will be big enough to do that, and hopefully one of the teams will actually do that. So that will put that debate to rest.
I'm frustrated by these papers that say things like, I can factor this faster using a VIC-20 than using a simulation of this quantum algorithm. It's a silly argument because the problem is getting error-corrected qubits at all. And then Shor's algorithm is polynomial time, so everything goes very fast after that point.
So will there be signs along the way, or will we suddenly have...
Do you want to say it to the mic?
Oh, sure. So will there be signs along the way, or will we suddenly have error correction factoring way bigger numbers than 21 and breaking all our cryptography?
I'm not the person to answer this. But from what I can tell, it's now just engineering.
So, I used to use this Moore's law model to try and predict the reason I used to say 2040 is you do a Moore's law calculation and you kind of get 2040. And after talking to the physicists again and again, they all seem to be of the opinion that Moore's law is the wrong model here. It's not, this stuff doesn't evolve linearly, but it evolves in jumps. It's like human flight, right? There was one day where humans couldn't fly, and the next day humans could fly. So the stuff evolves in jumps, and as a result, Moore's law is actually not a good model. So predicting has now become very difficult. And then will we see, you're asking also, will we see progress? That actually is a very touchy topic. Let's just say the fact that the Google paper had a zero-knowledge proof in it rather than the actual circuits suggests, and they're very clear about that, that there might not be as much transparency going forward as we have seen in the past. So it could be that, I don't mean to, I don't know, I'm not sure how to say it. I'll say it anyhow.
Yeah, say it.
Because that's what they're telling us, basically. It could be that like 5 years go by where we don't hear of any progress, but that doesn't mean that progress isn't being made.
And even when we do hear progress, that progress could be stale.
Well, on that note, this is actually, I've been getting signs for the last 15 minutes that I had 5 minutes each time. So I think it is probably a good moment to wrap up. We also brought you back onto the panel, so it was a full circle. I want to say thank you to all of the panelists, spontaneous panelists, for joining us. I want to say thank you to this entire audience. Thank you for coming to ZK Summit and joining us for another edition. Yeah, thanks so much. Oh, yeah. And we're not quite done yet. We actually, just sort of spontaneously as well, decided to grab a few drinks at the bar on us. So there is a tab. Please enjoy a few drinks in the lobby, and we'll get a chance to continue our conversations. Till next time, bye. Oh, that was an awkward end. Why did I do that?